And then I welcome our keynote speaker, Stefan Filipp, to share his screen and start his talk. Please.
Yes. So you should see now full screen, the presentation mode.
Yes, perfect.
Okay, perfect. Yes, so thanks a lot. Thanks a lot for the invitation. And I'm very happy actually to talk a little bit about, and actually Anton suggested to talk a bit about hidden qubits and wrapping the story kind of into the general context of beyond standard control of superconducting qubits. So from the title you see, we'll talk about superconducting qubits, probably not as a big surprise here. And beyond standard control means that we are investigating a little bit what can we do beyond this typical paradigm of that we are doing single qubit operations on all of the qubits and 2 qubit gates. What can we do beyond this? Can we use this somehow for getting more interesting features onto such a quantum processor? And that's roughly the story. So the experiments were partly already performed for full disclosure at IBM, where I worked before. And now I'm actually at the Walter Meissner Institute and at the Technical University of Munich, so in Germany, close to Munich. So, as mentioned, I will talk about superconducting qubits, and as you are aware of, I don't spend too much time on what these qubits are, but maybe just let me summarize why I find them nice. And that's basically these 3 last points, or these 4 last points that are kind of the technically nice features. We have fast gates. We can control them on nanosecond timescales. We can make these gate operations high fidelity, so that's an attractive feature. And we can operate them stably. So that means although we can operate them for 24 hours without much recalibration. And we can have scalable fabrication technology. Not going much into details, you know, we have a cryostat, we put in the package in there, we can put smaller processors, larger processors, chips, QPUs, or qubits in there. Here is a sample that we have currently also in our fridge with 3 qubits and a tunable coupler in them. Then we have the qubits. That's typically, and that's what we also use, is this Transmon style qubit with the 2 pads here, which are connected via this Josephson junction, where we can then have Cooper pairs hopping on and off, and we get the typical Transmon, this anharmonic spectrum. Sorry about my voice, a little bit troubles at the moment, but I think that will last until the end of the talk. So what is the state of the art? Just to bring this to your attention, what is kind of the game that we are in? We have now already first quantum computer prototypes on the market, more than hundreds, even 400 qubits, some better, some not so good, but in principle, we can have control over large systems. And I think that's really spectacular, because also now I'm a little bit longer in the field, and looking back, that was kind of unbelievable, maybe some 5 or 10 years. I think it was kind of, everybody thought about 1 or 2 qubit systems, 4 qubit systems or so. And now there's really a rapid progress towards scaling up systems. We see that there is mostly superconducting qubits on this very large number of qubits, Google and IBM. There is ion trap systems. There's many other platforms coming up and being in development, also different superconducting qubit processors. There's the European project. We have some German projects where we build large scale processors, and then clearly also the WACQT as one of the forefront technologies also in Europe in building up large scale quantum processors. We have seen already what is kind of milestone logical qubits, long-lived qubits is one of the things that everybody is after, but also practical quantum algorithms. And so that's just the context. Going towards these large scale systems, it seems that we have kind of reached a status where we can already tame lots of qubit, but the point is in making these actually useful, or making them a useful technology, or going even further than that. There's lots of challenges. There's lots of fun to play around the technology side and the physics side in tackling all of the challenges to go towards this error-corrected quantum computer. So let me mention a few of them and then go a bit more in detail what we investigated along these lines. So scaling, that's quite a general topic, but it's more on the technology side. if we think about large-scale devices, we have to take cross-couplings and crosstalk into account. If we have one qubit, two qubits, many qubits, we want to address them individually. We don't want to address all of them at once. Uniformity and reproducibility, in particular because it's man-made qubits. We have different junction areas, we have them different locations. So we have to make sure that we have the reproducibility, uniformity under control. And then it comes to scalable control. If you have multiple thousands or even 10,000, 100,000 of qubits, how do we can control these? How do these fit on a single chip? How do we get rid of all the heat that we send in by, for example, by flux pulsing? Then we have coherence. Coherence, we need to maximize the lifetime of quantum states, and we all know that's one of the most impeding or the most imminent question in how to avoid noise, how to identify lost channels. Prominent examples, many people are studying this right now, is two-level fluctuators. Where do they sit? What are these? What kind of noise are they causing? And how can we eliminate those? Quasi-particles, ionizing radiation is investigated, magnetic field fluctuations from surface spins, from external sources, and mainly also how to mitigate those, either by fabrication or by design. Another point, control and readout. It's not only coherence. We can maximize the coherence if you're doing not very well in the control of the qubits, then we don't have high fidelity gates. So we can look into pulse optimization. We did some work on that. I don't want to focus here on that. Investigating benchmarking sequences. How do we actually figure out what is a good gate? And then I will focus a bit on that. Addressing multiple qubits at once, extending basically the gate sets, the availability, the control that we have over the systems. The last point, and that's then really towards making the technology useful, is also we have to think in terms of a system. It's not good enough that we can control the qubits and do this for some times. We have to basically create stable operation conditions. That means we have to come up with operating systems, runtime environments, really make this into a system where we can run this as a computer in the usual sense, where we don't have to care about what's going on, but really make it available to users. So I'll address a few points. Coherence, for example, only briefly. There was a talk by Leon Koch from my group who told you a bit about what fabrication can do to improve coherence times. One can nowadays reach typically lifetimes of superconducting qubits around 200 microseconds or so even longer. And T2s equals T1s. So we got now, for some of the samples, 400 microseconds or so. And that's kind of tells us also that it's with doing basically all the homework and fabrication, we'll get to a nice and long-lived coherence. But it's also then the question is how to integrate this into the larger setting. And that's then basically also the scaling effort. We have to guarantee that it's performance at scale. This is what I want to focus, and I want to focus on this particular aspect. I want to focus on this control and the input-output. So here we did some work and thinking about how to deal with this addressability question. Some requirements for scalability are reduction of modes in large chips. That's one of the things is if you grow your chips larger and larger, then you have microwaves and you have standing microwave modes in this chip. So you have to think about how to reduce this. This can be done in 3D integrated setups. You have these TSVs here. Sorry. Let me just find the pointer. You have the TSVs to reduce modes. You have to reduce crosstalks. Can be done via bump bonds, so basically connections that basically shield the wires. But still, we need to address all of the qubits, and that means for large-scale processors, thinking about the universal quantum computer with millions of qubits, we need also millions of control lines. Now that's okay. You can ask now, when does this become really a challenge? Can say now for specific for lower numbers of qubits, like what we have right now, a few hundreds or so. You can still do this with high density wiring, such as brute forcing basically lots of cables, microwave cables into the fridge. That will work until, say, 1,000 qubits. I think that should probably work. And companies are focusing on building up cable trees which feature lots of cables. Then you can think beyond that. What is technologies that are that are there? People are investigating cryogenic electronics, be it RSFQ circuits, CMOS circuits. It's not clear at the moment which will win or whether that's all become useful. It's probably the heat load onto the stages is actually a challenge to bring this under control. But that's kind of interesting investigations how we can use electronics at the cold stages of the fridge. Multiplexing in general, so having so like we do for readout, also for the control qubits, we could think about this. Another way is we could use not microwave cables, but use optical fibers. There's some really interesting experiments now going on in sending in optical signals, optical photons at photodiodes, and then controlling with these the quantum circuits. And what one could also investigate, and this we studied a bit, is do we need to control all of the qubits? Or can we actually sacrifice some control and still be able to get a quantum processor to work? So that's what I will talk a little bit here. So let's take a step back. What is the typical assumption that we are having? We're assuming that all of the qubits are SU2 controllable, meaning that we have single individual qubit control for each of the qubits. And the question is, can we sacrifice some of the control, but still execute complex algorithms? What would be the pros? What would be the cons? So a pro is definitely that we would have simpler hardware, less control, less readout lines, less space required for them. We could also think about, since this qubit is hidden here, there's better protection against environmental noise. Clearly, the disadvantages, we would need more operations because we need to actually deal with, we have to get the control to this one via the coupling to this control qubit. And it's also less obvious how we calibrate this qubit. So the scenario that I'm discussing now is, so we're going from this setup where we have qubits in chains or also in 2D setups, coupled via a coupling element. And now each of these qubits has a readout resonator here on the left side. And we want to go to a situation where there is one qubit that is controllable and where we can do readout. We have coupler to a qubit that is hidden because there is no control and no readout. And also this one here. And then this one controls then this one. So we kind of have a setting where we can control all of the qubits. What does this mean in a 2D setting? Just also to look into numbers. For example, if we have this array here, then that would mean for 50 qubits in a square array in the usual setting, assuming now that we need 3 controls. So we need a microwave control, we need a readout, and we need one control line for the coupling. So that would mean 150 controls, 50 readouts for 50 qubits. We could reduce this in the setting that I showed before, so where only every second qubit is controllable, to 110 controls, still enough, but only 10 readouts. So because the controls also go to the couplers, so there's a significant reduction in the number of readouts. And we can play this along and even extend this setup and say, what if we attach now more qubits to one control qubit? So, but what we need to figure out is basically how the control works now for the setting where we have one control and one hidden qubit. By the way, this could also be applicable to other systems. So there is, if you look into spin quantum dots, there this control problem is even a little bit more prominent because the structures are much smaller. So quantum dots works on the tens of nanometer scales, and then you have a huge fan out. So that means you have to get more classical control into a more denser packaging. And this could be also then relevant for these kind of systems. So what does it mean for the control side? let's look at the readout first. So for the readout, what do we have to do? Which operators do we need to read out? And how do we achieve reading out all of the operators to do, for example, think about state tomography. When we have a measurement operator that you want to get the expectation value, then what we typically do is we are applying some unitary transformation onto this row and to evaluate this trace of the state. The group of the unitary transformations must be complete. So we must be able to get all possible measurement operators from a given measurement operator that is composed of the sigma c's. So in this term, in terms of superconducting qubits, we have sigma c's operator acting on the first qubit, on the second qubit, or this correlator sigma c for measuring the expectation value of both qubits at the same time. Applying our unitary operators to this one here, we can now implement a full set of measurements to get hold or to evaluate all the correlators that we need. And this, if we have now these 4 operators, so if we can measure the single qubits here and here, and the correlator, and apply now unitary operations on the individual qubits, indicated here by these arrows. So here's X and Y operations to go from a sigma C operator to a sigma Y operator or to a sigma X operator, and that in all rows, and from here to up, so we can get all of these correlators. How does this change? How does this change if we say we cannot read out the second qubit? That means we only have one of these measurement operators. We only have sigma C on the first qubit, but not on the second qubit. Still, for doing full state tomography, we need to get, by some unitary transformation, we need to be able to implement all of these operators. With single qubit operations, we can only get that far. We can only go from here to a sigma, from a sigma C to a sigma Y or to a sigma X, but we cannot go down in this array. What we need, clearly, we need extra 2 qubit gates. And the question is, how many do we need? If we have a C phase gate, that could bring us along this column here. So we could create now from sigma Y operators and the identity, we get to a sigma Y, sigma X, and so on and so forth. But that's not enough. That doesn't cover the full set of correlators. We need some extra, so we need another gate. We need an I-swap gate that brings us now to each of these correlators, starting from this initial ones where we could only read out one of the qubits. So that tells us that we need, instead of now having control or readout capabilities of the second qubit, we need to implement 2 types of 2 qubit gates, a C phase and an I-swap gate. And then we can actually sacrifice the second readout. The same story actually holds for the 2 qubit control. If you have single qubit gates on one qubit, Rx, so some operator which rotates about the x-axis, one which rotates about the y-axis, then we get this set of operators that act on the qubits. So the first qubit, one is sigma x, a sigma y, and a sigma c. If you have a C phase gate, then by commuting and figuring out what kind of operators one has available, then one sees that there is this bottom row here, the sigma x, sigma c, sigma y, sigma c, and sigma c comes into the game, but we don't cover this set here. If we have add an I-swap, then we also can almost fully control the system, but there is some empty points here which we cannot reach. So only a C phase gate or only an I-swap gate doesn't give us full controllability. It's only if we combine now having this I-swap and the C phase gate, then we can fully control the system and basically do any operation in this SU4, so this 2 qubit subspace. Note also that if we would have a different type of gate, which we don't have in the superconducting qubit platform, some square root swap type gate without the I in front, corresponding to this XXYYCC interaction, And this would actually be sufficient for full controllability, but rather difficult to realize on this platform. So where do we get this gate? The gate that we were using is the parametric gate, using a flux-tunable qubit as coupling element. So here we have a qubit 1, a qubit 2, a tunable coupler in between. And what we can do now, you can also look here, there's a tunable coupler. We can now change the frequency of this tunable coupler by threading a flux to it. What this changes, it changes this J, this effective coupling between the qubits. It changes it as a function of this frequency of the detuning of the qubit from the tunable coupler. And here we can add some harmonic modulation. So that can be a cosine of some frequency times t. So with this modulation of the squid loop, via the inductance, via the external flux, we can modulate the flux. This flux modulates the qubit coupler detuning, and this modulates the effective qubit-qubit coupling. And this we can use actually for implementing now parametric gates. More pictorially, what's done is, so here you see the coupler frequency as a function of the external flux applied. So if you apply now a harmonic modulation of the flux, and this translates into a modulation of the frequency of the coupler. And with this, we are getting a modulation of the coupling. And now it depends on the frequency at which we modulate now the coupler frequency. This then effectively implements different types of operations. So if you modulate at the qubits difference frequency, we are getting this I-swap operation. This I-swap operation does basically a swap between the 1-0 state and the 0-1 state, this red arrow. If you're modulating this coupler at the some frequency, then we are getting a sigma plus, sigma plus, sigma minus, sigma minus. So that's basically a 2-photon transition. We are creating or annihilating 2 photons, 2 excitation at the same time, which brings us from the Kraus state directly to the 1-1 state and back again. If we modulate now at the difference plus the anharmonicity frequency, so that means at this 1-1 to 0 transition, or we could also use the 0-2 transition to 1-1, so the 0-2 to 1-1 transition. And this would actually create an effective interaction between these ones. And with this, since we are only affecting the 1-1 gate, we can implement a CZ type interaction, so a C-phase gate. So we're kind of flexible in choosing now the frequency to implement different types of interactions. We tested this in experiment. So here's the qubit setting that we used. Qubits around 5-6 gigahertz, anharmonicities of 300 megahertz. The T1s were about 70 or 20, and T2s likewise. Coupler is a little bit worse here in terms of T1, T2s. And with this, we tested the different gates. We saw actually that both gates work fine to the level of the 1% at that, in this case. And the best fidelities we get around this 100 to 150 nanoseconds. It seems like there is not so much a difference between the I-swap and the CZ gate. In practice, turns out that the I-swap gate is more sensitive to errors and more sensitive to residual CC terms and also the phase stability of the drives. So that gives us here a little bit, so some other effects. But we investigated this a bit more carefully. But for these purposes, we see now that we can implement the I-swap and the CZ gate at the same time. So with this, we can now go ahead and implement now quantum process tomography on remote gates. So remote gates meaning now not far distance, but basically gates to and from this hidden qubit. So for quantum process tomography, we're doing some state preparation typically. We do the operation that we want to investigate, which we want to do a process tomography on, and then we measure. And now with this hidden qubit, we do the same thing, but we have to decompose now. For example, if we want to implement an X gate on the second qubit, we have to embed this into an I-swap between the first and the second qubit, do an X gate on the first qubit and an I-swap. And this we have to do for all of these operations. So that means that there's an overhead of operations. Still, in this gate, we are getting now the C-phase gate with a decent fidelity. So that is this gate. We're seeing now the Pauli transfer matrix, and we're getting this with a fidelity of 98%. Similarly, we can do a remote X gate. So like this one here, what we are showing as the unitary, and see that we can reach high fidelities of 99%, even though we have to decompose all these operations. This fidelity, it's another story. We have to actually extract from an iterative, a self-consistent procedure. We don't have now full control because we cannot read out actually the second qubit. And also the phase of the hidden qubit is actually undetermined. So we actually save one of the, so we have one parameter less in the system. But that's just to note at the side. We then investigated basically how does this scale if we now couple more of these hidden qubits. We did this on a theoretical basis. So if we now add more and more control qubits, what would be the steps per circuit layer if you think about, for example, a benchmark measurement which is used for quantum volume measurements, where you have now this SU2 operations in one layer on a number of qubits on this vertical, and here you have different circuit layers N where we have pairwise interactions. So how does this decompose into number of actual operations that we have to do if the qubits, if these SU2 operations have to work between distant qubits? Then we see for H equals 0, so that means that there is no hidden qubits. We get the typical scaling behavior of n square root n. So that just means that when we have to create entanglement or do some SU4 operation between distant qubits, it typically scales with square root n. So basically the diagonal to reach each of these to reach a distant qubit. This scales a little bit unfavorably if we add now qubits. It scales with n squared because actually we have a bottleneck here. We have the control bottleneck because we always, when trying to do something on this hidden qubit, we have to go over this control qubit, and that leads to a n squared scaling. We also investigated then what does this mean in terms of quantum volume. So quantum volume being basically the measure of how many steps, how many layers can you execute until you get garbage for a certain number of qubits in this vertical direction. So if you do now this and assume now a certain error per gate. So assuming now that the 2 qubit gates have a certain errors, the single qubits are perfect, here at the level of 1%. Then if we look at this graph, and this graph shows us now the number of control lines on the x-axis. So here basically is the system size in terms of number of control lines. On the y-axis, we have the hidden qubits per control qubit. And we see then here as these lines here, this dashed lines, we see then the number of qubits that comes with the number of control lines. So for example, if we have 0 hidden qubits, then 50 control lines could control 20 qubits. So that's what this graph tells us. And then we plot on the z-axis, so as the contours, we plot the quantum volume. And what we see here is that for 1% error, the quantum volume is low. We cannot basically do anything. We can only do some very restricted control of a very small number of qubits at all. And this doesn't change with adding hidden qubits. If we go to more future error rates, so say we can reduce the error to 5 nines, 99.999 on the 2 qubits, then we see actually that we can actually get decent quantum volumes for hidden qubits, for 0 hidden qubits. Here we see the red areas with large quantum volume. And we also see that in this case, we can actually sacrifice control lines. We can go along this line here and add 1 or 2 hidden qubits without sacrificing too much the quantum volume. So in this setting, we have actually good qubits. We could actually expect a higher quantum volume with the hidden qubits for medium-sized devices with low error rates. And here it would basically be a benefit because then we can save on the number of controls. So now, Anton, I'm running out of time, I guess. I kind of completely.
You can take another 3 or 4 minutes if you like.
Yeah, exactly. So, but I cannot basically finish with the second topic that I wanted to discuss, which was then the other thing is, how can we actually, in larger system, extend the gate set and use multi-qubit operations? So basically, I'm just telling a little bit what is the motivation, and then show you the results that we are doing in this direction.
Okay.
So with larger systems, now as said, we have to be able to actually control all of the qubits, and we want to avoid basically the bottleneck that we have because of low connectivity and only local operations. So here, for example, in this line, we have low connectivity between the qubits. If you want to entangle this one with this one, it might take a while because we have to do many swap operations. We can implement the multi-qubit operations and non-local operations. There's a literature on that, and also some nice experiments done in Chalmers on that, on multi-qubit couplers. And we are also working on this in our lab. And the other thing is, we can look at how can we actually simultaneously switch on interactions between all of the qubits and transfer information, and doing state transfer or swapping this qubit in an efficient way by simultaneously switching on all the operations at once. And then we investigated basically what is the expected speed up and how can we implement this fractional state transfer. The Hamiltonian is then basically we having a line of qubits. We add this nearest neighbor couplings, and we can choose now which frequency the qubits are in, or at which detunings they are, and what couplings are between the qubits. And then, making a long story short, we see now actually that we can, by switching on the interaction at once, we can implement now an operation which acts between the first qubit along this line and the last qubit, or in more generality, between pairs of qubits, symmetric pairs, at once, and we can transfer now, we can make swap operations between these pairs of qubits, between qubit 1 and n. So by choosing this, for example, look at this graph here. There is an excitation in the first qubit. By setting now the frequencies and the couplings correctly, we can implement now a swap between this first qubit and, in this case, the qubit number 15. So we can make a full swap in this on this Bloch sphere. If we want to do a fractional state transfer, so we're making a pi-half rotation, we choose these values differently, and you see this in this graph as a function of runtime. We start with one excitation here and end up with half-half superposition of the excitation being in qubit 1 or 15. That happens in all pairs. We can do this on many pairs. We can use this then, I don't now go in details, but then show you basically the results. We can use this for parity measurements. We can use this for fermion simulations and also for multi-qubit gates. But what I want to show you at the end is also the experimental results that we are doing right now. We can make this state transfer on a 3-qubit chip. Here is the parameters. T1s are here around 20 or so. And that's what we are seeing here. So we are seeing nicely that if we can control now these qubits and switch on this, the couplings between the qubits, we get this state transfer from qubit 1, starting here. And then we go to qubit 3 and back and forth and back and forth. So basically seeing this oscillation between the population of the first qubit and the third qubit. We can also implement this fractional state transfer by setting the values differently. And you see some slightly more complicated shapes, but that just tells us that after this time tau, we get now a fraction of the state is being transferred from qubit 1 here to qubit 3. Implementing this rotation about the x-axis of this sphere. And that works pretty nicely. We also checked that the rotation angles are according to theory. We checked then also that the transfer time is less than if we were to decompose this. So that's the decomposition line. And we see that we are a factor of 2 or so faster by doing the simultaneous interaction. We're currently looking into this in larger setups. We're having now a ring setup where we have 6 qubits, And in this 6-qubit setup, we are now doing swap chains between more qubits and basically implementing this on larger setups. That's basically the end of the story. I've talked about the control of hidden qubits where we don't have hidden individual control. How can we reduce possibly control lines? And also how can we implement different types of gates for making a more efficient entanglement on a larger chip. Outlook is we want to study this also with multiple excitations. We want to demonstrate and use this, for example, for parity measurements. And that's basically the next steps that we will pursue. We are doing this a little bit of advertisement in our Munich Quantum Valley. So we're also going towards this large scale devices in the near future to come. Intention here is also to build a full stack quantum computer in collaboration with different entities. Here, actually, not only the superconducting qubits, we're also having neutral atom qubits. Quantum computing, that's basically the main aim, building a universal quantum computer. It's a grand challenge, I would say. It's great fun. And if you are interested, I want to thank the members of the team that worked on this project. If you're interested to join, also drop us a line. Thanks for listening.
Thank you very much, Stefan. I suggest everyone who wants to clap, you can unmute and clap. All right, so we have time for 1 or 2 questions, I think. Raise your hand, or send a message in the chat if you want to ask a question. So I see a lot of clapping hands. Let's see, do I see any raised hands? Okay, I can ask a question in the meantime. So I was wondering, with these hidden qubits, you talked a bit later about connectivity. Like, can you increase connectivity by using these hidden qubits somehow? Like usually an obstacle to high connectivity can be frequency crowding and stuff, right? But I'm wondering if that becomes different somehow if you have these hidden qubits.
Yeah, I didn't think about this, but I guess you are right, because I mean, what you are also avoiding, or you can, I mean, is it a design choice? Probably it's also then a design issue that you can hiding. It also means that you can hide it from microwave lines, because you can probably more encapsulate them. And that's also one of the things that we have in mind, and you could use them basically as some kind of memory, but you try to reduce the coupling as much as possible and make the highest coherence as possible. Because one of the bottleneck or one of the challenges is that typically you couple the qubits to some feed line or so, and then you have some channel of decay. So this could be one thing. And I guess that also goes in the direction that you were saying, because then you also avoid kind of frequency collisions, because you don't care about these hidden qubits, because they also won't couple that much to other next nearest neighbor qubits. So yes, I think would be an interesting thought to actually think about what this means in terms of frequency crowding. Yeah,
I guess I mean, what you gain in if you gain in connectivity, you might lose it in the sort of the longer sequences of gates you need to control this, but it's interesting to think about.
That's kind of the thing that one figures out. It's kind of the loss is also so that the number of gates that you add, basically that you need, kind of is significant. So you need really good coherence, basically, to actually eliminate this overhead, or basically so that you don't have this overhead as the dominant factor in your overall fidelity.
Yeah. Okay, let's see. Was there any other raised hand for questions?
I had a question, but partly you answered in the end. Like, it was about the frequency crowding. So does it even actually solve, like, when we need to do the gate operations? Because yeah, with the hidden qubits we don't need to care about their frequencies, because they're isolated, but during the operation, does it come into the action? Like if you want to do ISWAPs?
No, I think so. So for this 2-qubit gates between the control and the hidden qubit, it doesn't play a role because there you have the frequency crowding issue as you have by two normally coupled or in the standard setup.
Yeah.
I think it only would help if you say like you have now also some influence of the other qubit that is also connected directly. So of some spectator qubits or so, that you would drive them as well with the tunable coupler.
Ah, I see. Okay.
I think it might be a good point actually to add some isolation, and that you could probably achieve. So we didn't look into that, but yeah, as mentioned, could be an interesting point.
Okay, thanks.
Okay, then I think we thank Stefan again, and next speaker, James Teoh, are you ready?
Yeah, can everyone hear me? Okay.
Sounds great. So you can start sharing. Yes. So yes, next speaker is James Teoh from Yale, who will tell us about dual rail encoding. Please take it away.
Thanks, Anton. So yeah, my name is James. I'm a graduate student with the Rob Shokol lab at Yale, and this talk will be about this proposal for a new architecture in superconducting circuits, where we envision using the dual rail encoding to store the quantum information. And what this enables us to do is essentially detect errors as they occur at the hardware level. And overall, we think this gives us kind of a new avenue to getting error rates that are like far below the thresholds for error correction, without having to necessarily like improve much on today's coherence times, which tends to limit current operations. So yeah, this work is based on this proposal shown in bold, but also draws on some other preprints from our group on the archive recently. So just to jump into it, so we're deciding on what we should use as our physical qubit. And the requirements for this kind of vary across various quantum computing platforms. But at the end of the day, you want to make sure that your error rates and the various operations you do, like measurements, gates, etc., are significantly far below the threshold for some error correction scheme, as you concatenate these physical qubits to build some logical qubit that hopefully has a much lower error rate than the physical error rate of the physical qubits themselves. And people have been looking at this approach in various platforms. I'm just highlighting Transmon kind of surface code architectures, which we kind of is kind of what we're comparing our approach to, where the single qubit gates, they're far below threshold. The 2-qubit gates, they can also be below the threshold, which is about 1% per gate for the surface code. But of course, as you scale these system ups, what's been found is that you tend to end up with error rates pretty close to the threshold, and as such, you don't see improvement yet as you increase the distance of the code. So what we're going to do is we're going to introduce an alternative system for our physical qubit that is also going to use transmons, but not as the physical qubits themselves, but rather as ancillary systems to control microwave cavities. We're going to use this to do the dual rail code, and the idea as to why we think this can be an easier route to below threshold operation is that the microwave cavities by themselves, they have good coherence times, and they tend to just be spoilt by the transmons. And the other thing that we've realized is that if we can detect the hardware errors as they happen, things like photon loss in the cavities, Pauli errors like phase flips and decay in the transmons, then this can give us an easier route to error correction by the idea that now we have to deal with erasure errors. We know where and when the errors happen. So just an introduction about these microwave cavities, why they could make good physical qubits. So here I'm showing a 3D stub cavity, which is one way to implement a superconducting microwave cavity. And these are essentially harmonic oscillators, and their coherence times can be pretty good. There's pretty much just one error channel, which is photon loss, or T1, which can be around a millisecond. If you further optimize this, then yeah, the coherence times of these cavities are pretty good. The dominant channel does indeed seem to be just photon loss, and the intrinsic dephasing rate is thought to be very low. In other words, these systems already have an intrinsic noise bias. Now, the trouble with these systems, of course, is that they're harmonic oscillators. So by themselves, it's very difficult to do quantum control, and you usually need we needed some other source of non-linearity that will let you prepare and manipulate quantum states. And so what has been done for almost the past decade or so, what is usually done is that we introduce the non-linearity in a way that it is, in this particular example, is by dispersively coupling an ancillar transmon. So experimentally, this is pretty easy to do and amounts to kind of sticking in a transmon to couple to the cavity mode. And if we're in the strong dispersive regime, then what you get is this dispersive coupling between the cavity and the transmon, which is the resource most commonly used for quantum control there's a whole extensive work on over the years of how to do control, essentially based on this Hamiltonian. The trouble with this approach, though, is that the speed at which you can do things like gates is limited in some way by the value of chi, the strength of the dispersive interaction. And typically gate times are about a microsecond. If we look, the other problem is that when errors happen in the transmon ancilla, such as decay or dephasing, these tend to just propagate onto the cavity. And so just taking the ratio of the gate time to the coherence time, in a lot of these approaches, what we find is that it is the transmon that are limiting these gate errors to a 1% or larger. So one of the main problems that the dual rail code tackles is this problem of how do we get around the transmons propagating errors onto the cavities without introducing too much additional complexity. Okay, so now we're in the position to introduce the dual rail encoding. So here what we envision is that we are going to, it's the same as the dual rail code in optics, except we are now the information lives in the standing wave modes of microwave cavities, and logical 1 is going to be the cavity in cavity mode A, logical 2, the photon is in cavity mode B, and this is going to form our subspace. In addition, we will still have a dispersively coupled ancilla. That's going to provide the source of nonlinearity that lets us do gates quickly without having to resort to measurement-based schemes or the likes. And the philosophy behind this approach is that we are going to error detect as many hardware level errors as possible without the need for further additional hardware or concatenation. We're going to do measurements, and the idea is that throughout all the gates and measurements that we do, we will be able to flag photon loss errors in the cavity, which will be decay to 0, 0. Transmon dephasing, will detect that by measuring the transmon to be in the E state, and transmon to decay will be measuring the transmon in the F state. For this to work, we'll also be operating our transmon in its GF manifold, which lets us use that E state to detect decay. And the idea is that we're going to design a whole set of operations around this philosophy. And the idea is that if you error detect these errors to first order, then those become erasure errors, and the remaining errors you don't detect, which could be due to double jumps, for instance, will go into a remaining Pauli error that will be second order suppressed. So let's get into what we can do today with the dual rail code. So a nice property about the dual rail encoding compared to maybe some other bosonic codes is that the single qubit gates are incredibly recently have been shown to be pretty easy to implement with a beam splitter coupling. So the idea is that this will be like some parametric converter of sorts. You can turn on and off this interaction, you have phase control, and this is rather analogous to the charge drive for a regular transmon. And what's been shown recently in the group by my colleagues here is that by using this particular RF squid coupler, you can do gates in the dual rail encoding that are already approaching 4 nines of fidelity. This is after you detect for photon loss. And for this particular gate, you don't actually need the transmon ancilla at all. All the non-linear elements in the system can stay in the in their ground state. And so you're this is already like naturally robust to errors. Yeah, and as I mentioned, with this driver, you can kind of do arbitrary rotations in the blocks fit. So we're going through a checklist for a new physical qubit, and I just went over some single qubit gates. State preparation in the dual rail code is pretty simple. It amounts to preparing a single photon in one of the cavities, which has some natural robustness to Transmon errors that may occur, and has been demonstrated with a few approaches I'm citing here. State readout is also fairly simple, but I won't go into detail here. What I'll focus on next are the operations where you are more prone to errors in the ancilla transmon, but still have this error detection property. Namely, this is the ability to non-destructively measure if a photon loss has occurred or not in the dual rail code, because we need to we need to detect that error and reset the dual rail qubit. And also, of course, how do we do the entangling gates, which is a bit less obvious. So here, what I'm showing is the kind of hardware on the left that you would need to implement like a physical dual rail qubit. And what we notice is that in order to do, in this case, the photon loss detection, the hardware components we need are, again, just the beam splitter interaction and a Transmon ancilla. And the idea is that we will engineer a non-destructive joint parity measurement with the system. Roughly how it works is the Transmon ancilla that is dispersively coupled to one cavity. It is fairly easy to do a photon number parity measurement. If we also turn on the beam splitter at the same time, then the photon swaps back and forth, and you can show that that there's a way to measure the joint parity information in a QND manner, which is the subject of this preprint here. So again, this is going to have the same error detection properties that I had earlier. Like at the end of this operation, you measure if you're in G, you're still in the code space, everything's good. If you're in E, then you had a Transmon error. If you're in F, you leaked to 0, 0, or you had a Transmon dephasing error. The idea is that everything's fine as long as you're in G. You still like preserve coherence in the dual rail subspace. Similarly, we can use the same operation to do our entangling gate. Here, our native entangling gate is this ZZ of theta gate. You can think of it as pretty much a C phase gate. And again, it's going to be built on the ability to do this like controlled joint parity unitary. What's nice about the dual rail code is that you only need like half of the cavities to interact, as long as you pick one cavity from one dual rail and one cavity from the other dual rail. Then you can do a 2-qubit gate on both of the dual rail qubits. And again, you can show that this also has the same error detection property. It's worth mentioning that in these constructions, you cannot like fully correct for the errors when they occur, but you can reset the qubits, and this is why it's kind of easier to do experimentally. So how should we think about this for kind of larger scale error correction? What does this mean for like an error correcting code? And for this, it's helpful to think of what we've termed the error hierarchy. So in general, if you're building some composite system out of transmons and microwave cavities and looking at doing some kind of bosonic qubit, then right off the bat, this is the kind of error rates that you expect. So if your operations are limited to around a microsecond, then your dominant error will be Transmon errors. These will be around 1%, depending on the exact coherence times, and it will be difficult to do something that is significantly below the Pauli threshold, which is marked on here with the blue dashed line. On the other hand, the cavity has better coherence times, in the sense that the T1 of the cavity tends to be around 10 times higher than the transmons. But the main sources of error is cavity photon loss, which will in general take you out of some logical subspace that you choose to encode your qubit. So for now, I'm just going to say this contributes to a leakage error. So it's also something that you want to address. And then the cavity dephasing intrinsically is thought to be very small and pretty much just limited by other modes like transmons heating up. And the colors here just indicate the type of error that the next layer of error correcting code would see due to these errors at the physical errors. So if we do this error detection, we're doing it at the hardware level, so we're not going to the next layer yet. Then the first order errors in the Transmon are now detected. And so these can be flagged as erasure errors to the next layer of hardware. And you'll be left with a background of second order errors that you miss. For instance, let's say you decay twice in the Transmon, but that happens at a much suppressed rate. So that will contribute to the Pauli error, but will be suppressed by roughly 2 orders of magnitude, we think. And that brings it below the Pauli threshold. So if we just detect for the Transmon errors, then we're already doing pretty well, but we still have this problem that this leakage in the cavity will inevitably build up. So to deal with this is why we also need to check for the photon loss errors that happen in the cavity, such that we can reset, add energy back to the system as it decays out. And thus we can have some constant fraction of qubits that are leaked. So just for the last part of the talk, I will discuss how this general approach can fit into a surface code. So here I'm showing a possible kind of...
You're running a bit short on time, so...
Okay, sure. Yeah, so so this is just one way that you could use this in a surface code. For instance, just showing the physical unit cell in black. And then my last slide here is that the idea of erasure errors is in a surface code is that you can essentially detect twice as many of them, and they have a higher threshold. And this is a property that's been noticed in many platforms, and now we're like using this in for our superconducting cavities. So yeah, the end message is that essentially with this error detection at the hardware level, we think we can get below each of the erasure and Pauli thresholds respectively. And you don't need to, we can achieve this with today's coherence times. All right, yeah, that brings us to our last slide. Yeah, I'll just wrap up here because I'm short on time, and we'll take questions.
Thank you very much. Let's unmute and clap to thank James for a nice talk. Do we have a question? I think we have time for one question at least. You can raise your hand or you can send the question in the chat. Well, I guess we are all curious to know if there are any experimental results on this. Is that something you can
Yeah,
say?
so the main experimental results we have so far are for the single qubit gates. So this is experimental data, randomized benchmarking of single qubit gates in a dual rail code taken by my colleagues here. So yeah, this is a pretty promising first result because we're already approaching 4.9 single qubit gate fidelities. One of the main assumptions of this scheme is that you can do a very good, very clean beam splitter that is only coherence limited, and this data supports that this is possible to realize. We're working on implementing other the 2 qubit gates are the next thing we're working on implementing, because that seems to be the most difficult one to get right.
All right. Yeah, looking forward to results from that. Thank you very much again, James. And
thanks, Anton.
Next speaker is Shahnawaz Ahmed from Chalmers, who will tell us about quantum process tomography. So now we see. Oh, it looks good.
You're muted.
You are muted, Shahnawaz.
Can you hear me now?
Yes.
Yeah. Okay. Hi, I'm Shahnawaz. I'm actually Anton's PhD student here at WACQT. And I'm going to talk about a new technique for process tomography that's now actually published, and the code is available, that we worked on last year. And here is the outline of the talk. And if you want to play around with the code or look at the paper, this is the reference of the paper. So I will first introduce why reconstructing quantum states and processes is an interesting problem. How can you look at it as an inversion of a linear system of equations? And then describe some of the problems with this inversion or the quantum process tomography, and show our approach to it, which is using a gradient-based optimization technique that is restricted to respect some physical constraints that quantum processors should have. And then show the benchmarks with techniques such as compressed sensing and projected least squares approach, and present summary. But before actually starting with the topic, actually we came around we arrived here because of trying to apply machine learning techniques in order to solve quantum process tomography tasks. And why machine learning? Because they're getting, like, they're in the news, of course, but they're also very much useful at solving different kinds of scientific problems and learning patterns, but then also, for example, protein folding and things like that. And so we were interested in seeing, can machine learning help in these kind of tomography problems? And we have a previous work on state tomography with neural networks. Why would one want to kind of look at machine learning for this kind of problems? One of the issues is that when you actually do experiments, the data contains a lot of noise. So here, for example, this is from one of our previous papers. This is the Wigner function of a certain state that was prepared in the lab, and you want to understand what's the density matrix that gives you this Wigner function. And you can already see that this was what was supposed to be the state. It got rotated a little bit. You have some noisy corners and everything. And it gets very tricky to kind of put all this information in your optimization. But you know, as a human, just by looking at this pattern, that no, this is the same state as this, is just has some rotation and other things. The same way, like, this is another experiment that's going on, and we're trying to do something with it, is like, if you are given this data and maybe you have experimental difficulties in measuring everything, you can kind of guess what is here, what should be filled in, but it's very difficult to find straightforward algorithms that do it. So the underlying message is that there is a lot of structure that exists in different kinds of quantum states processes. Can we exploit them? Can we teach algorithms to learn these structures? So, for example, a cat state with two blobs and some interference fringes in the middle, and then do something better than maximum likelihood or these other techniques that are getting used. And it turns out we can, and these are some of the references where we used, let's say, machine learning in some sense in these two papers, but also ideas from machine learning to do different kinds of things. And I'm going to talk about this one specifically. So let's break down what is at the heart of the current machine learning success. And to me, it is the tool basically are these three things. You hear a lot about neural networks. Let's just call them very expressive models that can capture everything that you have in your data. But at the heart of it lies the gradient descent algorithm. It's an optimization algorithm that gives you, from a family of these models, what's the correct model that fits your purpose. And the last thing that gets swept under the rug is all this magic that people do, regularization and other very specific tricks of how do you optimize, how do you choose learning rate, what kind of things, normalizations you use, and things like that. So if we take this machinery and try to apply it to the problem of quantum process tomography, what happens? So, and then more specifically, we use the gradient descent part and some modifications to it instead of neural networks and doing black box magic. So let's look at the quantum process tomography problem. The idea is that you have a quantum state, you apply some operation on this quantum state, and you arrive at a new quantum state. You want to learn what this operation is from some information that you collect. So what you do is you prepare different kinds of input states, the probe states, you apply them to this process, the black box, you collect some data by making measurements. And then the idea is, from this measurement data and the knowledge of what probes you have prepared and what measurements you have performed, you want to learn what is this object, this process that you have applied. And you can actually see that this is a completely linear problem. If you write all the steps to it, getting the probabilities is the Born rule, is a trace operation, which is a linear operation. How the process acts on it using the process tensor is also a linear operation. So you can kind of flatten this whole system out by writing, like choosing your process representation. If you choose it as this so-called Choi matrix, you can write this whole thing out as a linear problem. And the idea is solve for the Choi matrix, or the representation of the process, this equation where D is all the data, the probabilities, empirical probabilities that you've measured. A gives you information about which probes and measurements you have performed, and you want to invert this. But then, of course, you have constraints set by quantum mechanics that these should be completely positive trace-preserving operations. And this becomes very tricky. So the way that you can start thinking of doing this is just, let's apply linear inversion or least squares optimization or something. Turns out that when you have noise, it becomes very tricky to do this. If you have an undetermined kind of system, this also becomes complicated. And at the same time, there's no easy way to put all the constraints like complete positivity and trace preserving conditions on the least squares estimate. Then you have, like, this is for state tomography, maximum likelihood and different kinds of variants of it, super fast maximum likelihood, or this maximum likelihood minimum effort kind of techniques, but they're kind of expensive. You have also compressed sensing, which solves a convex optimization problem where it's very easy to put in the constraint of positive semi-definiteness or complete positivity and things like that. And there are lots of work that have done it. For state tomography also, it's very interesting because this is a technique that works with a fewer number of measurement bases than what you would otherwise need, because there's some regularization happening because of minimizing the norm. And for process tomography, you can also apply compressed sensing, and there's a new technique called projected least squares. And the idea is that you just optimize somehow and find an estimate and project it to complete positive trace preserving manifold. And there's this paper for a 7-qubit system, rank 2, they took like 3 days of processing time to do this, because this projection step requires some kind of eigen decomposition, discarding negative eigenvalues and things, and this gets really expensive. And to just give a scale of how expensive this gets is that, like, if you want to do like the basic thing of a 5-qubit process tomography, this data vector, if you measure all Pauli bases for all 5 qubits, this data vector is like 60 million. This A becomes 60 times 1. So inverting this kind of large systems becomes extremely time consuming and difficult. And people who have done this with compressed sensing for 2 qubits, it's easy. For 3 qubits, it like takes orders of magnitude higher, and it's a nightmare. So what is our idea? What did we try to see? We tried to understand this from a machine learning perspective, which is always trying to solve a kind of optimization problem where you have some loss function or objective that, given some data, a model or an ansatz, you try to optimize some loss within some constraint. So the ansatz that we choose is the set of Kraus operators to represent the channel. And so the benefit is that you have, like previously we had used neural networks as the model for it, but it doesn't give us so much control of what we are modeling. On the other hand, replacing, let's say, an abstract model like a neural network with the Kraus operators gives us a very physically meaningful constrained object that we are trying to understand and reconstruct. And then, of course, we use the gradient descent optimization algorithm, but we have to modify it a little bit because we have these physics constraints that tells you, let's say you apply gradient descent optimization here, it will give you a new set of Kraus operators. Like it says, okay, if you change your parameters like this, Kraus operators like this, you will now decrease this loss function. But what can happen is that now these new set of Kraus operators might not be valid Kraus operators that represent a quantum process. Then you have to put in some constraint. And this is precisely what we did in this work. And then it solves some other problems. And the other problem is that you don't have to write the full set of Kraus operators. You can have a low rank approximation to it and control this rank. So you don't kind of get drowned in computational processing where you are just maybe interested in the first few Kraus operators that perfectly reproduce your data, assuming that you have a few number of like a unitary and a few lost channels and things like that. Another nice feature of this thing is that you can now do batched kind of optimization. You don't have to look at all your data and invert the whole system in one go. You can send small batches of the data and try to iteratively optimize, get to a Kraus operator that represents the full data in the end, of course, but you do it batch by batch. And we use this idea from mathematics called manifold learning. So I will maybe very briefly mention, if you are not very familiar with Kraus operators and Choi matrices, it's just a way of writing a linear map where you can impose this complete positive trace preserving constraint. So for the Choi matrix, it's a n squared times n squared complex valued matrix that defines this linear operation in this way, where this is a partial trace. The Kraus operator is much more straightforward. It's a sum over k Kraus operators. These are complex matrices, and it represents a linear operation in this manner. The benefit is that these Kraus operators, you can choose how many Kraus operators to have, where at max it will be n squared. So then you can say, okay, I don't care about after the third Kraus operator, whatever it is. Now, the tricky part for this whole project was, how do you implement the trace preserving condition for Kraus operators? Because what you want is you want to optimize under this condition that k dagger k sum for all the Kraus operators gives you identity, because otherwise the trace preserving condition is violated. So you might end up with a physical process that increases or decreases trace. So once again, just to recap, we are using Kraus operators as our ansatz, and it has this benefit. We use this batch loss function, and then the Kraus operators give you a complete positive linear map by construction. And then we ensure this trace preserving constraint by using a technique called retraction or Riemannian optimization. And the idea is that this condition that you have on the Kraus operator, actually, if you just write it down, like you stack together all the Kraus operators in this long kind of matrix, this is basically an orthonormality condition. And this defines a so-called Stiefel manifold. And people have been thinking a lot about this, and they developed basically an optimization algorithm that ensures that you stay in the Stiefel manifold at each step of the optimization. And the idea is that, let's say you have this loss function, and the gradient of this loss function tells you to go in this direction. But if you go in this direction, you might jump out of the Stiefel manifold. So what you do is you try to find a path on the Stiefel manifold that still follows the gradient or the shadow of this gradient. So it's tangent at this point, but it stays on the Stiefel manifold. In some sense, you can think about like the Stiefel manifold, let's say if it's for 3 dimensions, real numbers, you want to optimize, but you want to stay on a surface, on a sphere, for example. And anything that tells you to go out of the sphere, you kind of fall back along the shadow and trace the path on the sphere. And the steps to do it is actually not so complicated. It's like 4 or 5 lines of code, a couple of lines of mathematical derivation using something called a retraction, which basically updates the gradient descent update rule. But I will not discuss maybe this thing in detail. And then you get like reap the benefits that that allows you to do something very interesting. So first benefit is it's fast. I have very little patience sometimes for algorithms, and if it runs for 3 or 4 days before you get one answer, it seems really inefficient to me. So it was very interesting that with the right tools, if you implement this, and you don't have to write anything yourself, because you have the whole neural network machine learning field that is optimizing gradient computation and writing good optimizers and making things fast. So you just write this with those tools, and you get for free a technique that runs within tens of seconds on a standard laptop for like a 5-qubit reconstruction. So this was also very interesting, because to do like 5-qubit reconstructions or set Hilbert space cutoffs of 3240 for compressed sensing or all these other techniques, it was extremely time consuming. We couldn't even go to 3 qubits in a matter of hour or something. So it was very interesting to see this was running extremely fast. Compared to some other techniques that are efficient, like projected least squares, you don't have this iterative eigendecomposition every time, because like the way that you project to the physical constraints is by guarantee due to the Kraus operators, and also due to this retraction, it's guaranteed. You do have some tricks that you have to play, but these are not as bad as doing eigen decomposition of a large showing matrix all the time. And then another interesting thing is you get some control over how much information do you even care about. You don't want to know maybe the full showing matrix where you might have very small elements or things like that. You might just want to know the most important part. So you can control this by saying, oh, let's reconstruct a rank 1, rank 2, rank 3. And after rank 3, if you see that there's no more improvement in the loss, that means you don't have enough information to distinguish the future, like these cross operators after rank 3 or 4 or something. And then, as I discussed before, like this batched way of optimization board from machine learning can handle a lot of data in a very nice and iterative way.
Shahnawaz, you
Yes.
are running a bit low on time. You should try to wrap up.
Yes, I think I'm done. I will skip this for time. This is interesting technique from math if you want to understand, but I will just skip to the result. And the result, for example, one simulation example is that imagine you have a continuous variable quantum process. You send in this probe translates to this one, and then you only very coarsely measure what is happening here. So this is the full detail of the state, but you only measured something like this. You can use this technique that we have to kind of reconstruct the underlying process, which gives you back what should happen. And this is really powerful because then experimentally, and this is a paper that is out now, you can kind of use this to reduce your experimental time, and you can take measurements in a very coarse grain, but still reconstruct the underlying process. And we benchmark this with compressed sensing, and we see that for, let's say, a full rank process, for 2 qubits rank 16 process, of course, if you don't have 16 Kraus operators, you are going to reproduce something that is not catching everything, like giving the full process. But still, you see that this is dependent on noise. If you have a high amount of noise in your data, if you have not sampled enough, then even if you take a very expressive model, you don't have enough information to distinguish it. So it saturates. So for practical use cases, there's a trade-off, how much you sample versus how expressive you model. And this was also doing the benefit of that it would work with a small fraction of the data. So like compressed sensing, you have this regularization trick that you don't need maybe the full informationally complete all basis information. You can, with 50% of the data, go to a reasonable fidelity. And then we kind of benchmark how many iterations it takes, how large a Hilbert space it can tackle. And it looks quite promising for practical use cases. And then the last part, and this is the last slide, we started with the previous project of using neural networks to do this. And then the idea in this project was, did we really need neural networks? What was at the heart of it? And we then tried to put back the neural network in this project and saw that using this Kraus operator ansatz was as good as using neural networks. And sometimes neural networks was giving unpredictable results also. So in this case, at least, neural networks didn't help or do anything better. So a well-founded ansatz was good enough with the gradient-based optimization. So in conclusion, we discussed one machine learning application for tomography, and the main message is that we should build in our physics knowledge, but borrow the techniques from machine learning maybe, and we don't need to use neural networks or black box things as a model because we have better models. And then in this technique, in this specific case, we could compare like the best of two worlds, compressed sensing and projected least squares, because like compressed sensing, it was able to reconstruct processes from little data, but could also work for large Hilbert spaces. Yeah, that's it. And these are the references. The code is available online.
Thank you very much, Shahnawaz. Let's unmute and clap to show our appreciation. All right, I think we have time for one question. Is there one question? Well, everything was crystal clear then. As Shahnawaz said, the code is on GitHub, and well, you can maybe send a message here to Shahnawaz in the chat if you come up with a question later. Yeah. So now we have a break until 7:40 Swedish time. So 20 minutes break, and then we continue with 5 more talks. So see you in 20 minutes. Welcome back after the break. We get started right away with Amir Karamlou from MIT, who will tell us about simulation of Bose-Hubbard lattice. So please, Amir, you can share your screen.
Okay, thank you, Anton. Yeah, let me start by sharing my screen. Okay, I'll begin. So hi, everyone. My name is Amir, and I'm a doctoral candidate at the Engineering Quantum Systems Lab at MIT. And today I'll be telling you a little bit about our results on probing entanglement across the energy spectrum of a hardcore Bose-Hubbard lattice. So before I get started with the content, I would like to take a moment to acknowledge our team, both at the MIT Engineering Quantum Systems Lab and also at the MIT Lincoln Laboratory, who've been helping us a lot with different things, especially including fabricating our samples. So with that, let's first talk about why we want to study many-body systems. Well, so interacting many-body quantum states are crucial to understanding condensed matter systems, black holes, and even quantum circuits. However, they're hard to study analytically and exponentially difficult to simulate with a classical computer. So it makes sense for us to use a controllable quantum platform to explore this physics. Now, one example of a many-body model is the hardcore Bose-Hubbard model, and I'll explain what that is in a moment. But in 2 dimensions, this model is non-integrable, meaning that we don't have an analytical solution or an analytical form for what happens with the system. Now, an experimental realization of the 2D hardcore Bose-Hubbard model offers insight about entanglement behavior and dynamics of many-body systems. So the sample that we use to explore this physics is a 3D integrated flip chip device fabricated by MIT Lincoln Laboratory, where the qubits sit on an independent layer, the qubit layer, and all of our signal lines, including the resonators, the flux lines, the Purcell filter, and the readout feed lines, sit on an interposer layer. And these 2 chips are essentially bump bonded on top of each other. Now, our device has 16 flux-tunable Transmon qubits, again, as false colored on the right side. Each Transmon qubit has a local flux line, which allows us to individually control the frequency of each site. And they're connected with a 2D connectivity with nearest neighbor coupling. Now, this system of 16 qubits is described by the Bose-Hubbard Hamiltonian, where the first term of the Hamiltonian is the site energy that's determined by the Transmon transition frequency. We have control by the virtue of the fact that we have tunable transmons, we have control over these epsilon terms. The second term is the on-site interaction, which comes from the fact that our transmons are anharmonic oscillators. So the strength of the on-site interaction, this U, is determined by the anharmonicity of our Transmon qubits. And then the final term is a coupling interaction, which again is determined by the nearest neighbor exchange coupling between the capacitively coupled qubits. Now, in our lattice, the magnitude of our on-site interaction energies, U, is much larger than our coupling interactions, J. And this allows us to emulate a hardcore Bose-Hubbard Hamiltonian, meaning that it's unlikely that we would populate that second excited state of a qubit just as a result of unitary time evolution if all the qubits either start in the ground state or the first excited state. Now, let's talk a little bit about entanglement and what it is and what we're trying to probe here. So in classical thermodynamics, entropy arises from uncertainty in the exact state of a physical system. Whereas in quantum mechanics, entropy arises due to entanglement among the constituent subsystems. So I can have a system, a quantum system, where I know the exact quantum state. And again, let's say it's isolated from the environment. However, if I look at a subpart of that subsystem of that overall system, Because of the entanglement between that subsystem system and the rest of the lattice, I will be lacking information, and that gives rise to entropy. Now, to see an example of this, let's assume that I have two subsystems A and B, and these two subsystems are in a product state, so there's no entanglement in between the two. Then I can write the overall state of my system as a tensor product of these two pure states. However, if there's entanglement between my subsystems, then this equality doesn't hold. So in fact, having just knowledge of one subsystem in absence of another will not provide me the knowledge that I need about the entirety of the system. And because of this, we can quantify entanglement within a quantum system by measuring the entropy of its subsystem, of its constituent subsystem. Now, we use a metric called the second Rene entropy to do this. And the second Rene entropy is the logarithm, basically takes a logarithm of the purity of the purity of a given subsystem, where this rho of X is the reduced density matrix of a given subsystem within our lattice when we trace out the rest of the system. Now, if there's no entanglement between the subsystem and the rest of the lattice, then rho of X will be a pure state. So then the Rene entropy that we'll measure will be 0. And again, that indicates that there's no entanglement between our subsystem and the rest of the system. Whereas if there's maximal entanglement between all the qubits within our subsystem, then the entropy of a subsystem will grow as the size, which I've denoted by V of X, and that's simply the number of qubits within the subsystem. So let's tie this back to the hardcore Bose-Hubbard model that we're interested in studying. So the hardcore Bose-Hubbard Hamiltonian can be represented as the following form, where the first term is just the exchange interaction between the qubits written in terms of two-level qubit operators. And the second term is the site energy, which is written in terms of the Pauli-Z operator. Now, the hardcore Bose-Hubbard model, or in general, even the Bose-Hubbard model, is particle number conserving. So if I start with 4 particles in my system, I will have 4 particles at any time as a result of unitary time evolution in the absence of decoherence. So because of that, I can write the Hamiltonian of this system and break it down into subspaces that are defined by a fixed particle number. Now, if I show you the energy spectrum of this Hamiltonian broken down in terms of the, trying to get the pointer, in terms of the different particle numbers, I get the following energy spectrum, where the color here highlights the density of states at different eigenenergies. And again, we can see that we have maximal energy bandwidth when the lattice is half filled, in this case, when we have 8 excitations, and then the bandwidth goes down as we get closer to 60. Now, we're interested in finding how does entropy scale depending on the system size for different energy eigenstates, or at different parts of the energy spectrum. So let's first consider a state right at the center of the energy spectrum. And in this case, I've chosen n is equal to 8, but of course, this entanglement trend will hold even for n is equal to 7, n is equal to 6, and so on. But right at the center of my energy band, or my energy spectrum, I see that my entanglement grows linearly with the system size until I reach around a subsystem that's equal to half of the system size, in which case it starts plateauing, and then afterwards it starts going down. Now, this curve form is referred to as a page curve. And what it indicates is that the entropy of my system typically grows as the size of the different subsystems within the lattice. So this is for a state right at the center of the energy band. Now I can also consider a state at the edge of my energy band. And what I see is that now my entanglement isn't growing as strongly with volume size. In fact, it's faring very weakly. So there's a difference in the nature of entanglement scaling within our system, depending on which part of the spectrum we're in. Okay, so now preparing each of these individual eigenstates is difficult because it will require an exponentially deep circuit. However, we can generate a coherent state-like superposition of the different eigenstates of the hardcore Bose-Hubbard Hamiltonian. And this superposition will have the same entanglement behavior because all these eigenenergies involved in the superposition will have similar entanglement behavior. Now we can do this by simultaneously driving the qubits in our lattice using the following Hamiltonian, and by changing the detuning between the drive of the subsystem, between the drive frequency and the lattice frequency, which is a frequency that all the qubits are at, we can occupy eigenenergies or eigenstates that are at energies along either the center of the lattice or closer to the edge. So by changing the frequency of the drive, we can generate many body states across the energy spectrum. And we can use this as a tool now to study the effective correlation lengths and entanglement behavior in our many body system. So the way that we drive our lattice, drive all of our qubits simultaneously, is by sending a drive through the common feed line that's coupled to each qubit via its resonator. Now, this drive will couple to every qubit with a different complex coefficient. We can characterize the magnitude of the drive coupling to each qubit by just performing Rabi sweeps, and we can characterize the phase of the coupling of the drive by performing interferometric like exchange experiments between different qubit pairs and reconstructing relative phases and then getting an overall phase reference to one of the qubits, the coupling of the drive to one of the qubits. Now, with that knowledge in mind, the first experiment that we try is just measuring the population of these coherent-like states. So for that, we drive the system again via the feed lines that are coupled to each qubit through its resonator on resonance. We can vary the overall strength of our drive by changing the amplitude of the global drive that we send to each qubit through its feed line. And then we measure the number of excitations in the lattice. And again, we denote that by n. So on the right side, I'm reporting the evolution, the dynamics of the total number of excitations in the lattice as a function of time. And what you notice here is that as the drive gets stronger, the dynamics gets a little faster, but in the steady state, in equilibrium, when I'm driving the qubits on resonance, the lattice will converge into being in the half-filling state. And in fact, I can look at the distribution of the measuring different number of photons within my lattice at 3 different times that I've highlighted as 1, 2, and 3. And we see that for a weak drive, when omega is equal to half a J, the distribution follows a Poisson distribution very closely for a truncated Fock space. And that's the reason why we call these states coherent-like states, because if you look at the population distribution of the number of photons within our system, they follow what we expect from a coherent state of light. Okay, so let's talk about correlations within our system now. So if I drive my system for long enough and weakly enough for the system to reach a steady state, I can then probe 2-point correlations along the x basis, again, denoted using the following equation. And here on the right side, I'm reporting the average correlator squared as a function of distance for different drive detunings. And again, remember, by changing the detuning of the drive, I'm accessing different parts, different regions of my energy spectrum. Now, using this data, I can extract the correlation length of my system by basically performing an exponential fit as a function of distance between my qubits. And what I see is that states at the center of the energy spectrum, especially when delta is equal to 0, when I drive on resonance, exhibit long-range correlations. In fact, the correlations are so long that I can't really quantify them properly within the limited system size that I have. However, as the states get closer to the edge of the energy spectrum, the correlations begin to become short-range. And this is a signature that there's something changing in terms of how different qubits are correlated within our system. But in order to properly quantify entanglement, again, we we use the second-order entropy that I mentioned a few slides ago for our system. And to do that, we measure the density matrix for different subsystems using simultaneous tomographic readout. And we do this for 163 unique subsystems within our overall lattice, up to a size of 6 qubits. And we look at the entanglement entropy scaling as a function of the system size, or V, for different drive detunings delta. And what we see is that states at the center of the energy spectrum, when delta is equal to 0, exhibit linear scaling with subsystem size, whereas states that as they get closer to the edge of the energy spectrum by increasing delta, show weaker and weaker dependence on the size of the subsystem. So next, we try to actually properly quantify this. And Anton, I see I have one more slide left.
Okay, great.
Yeah, this is, well, I mean, conclusion, of course, but this is the last one. So there are two different kinds of scaling with entanglement depending on the system geometry or the subsystem geometry. One of them is volume loss scaling, where the subsystem entropy grows proportional to the bulk size or the number of qubits. Now, this intuitively makes sense. In the classical world, if I fit more transistors, on a quantum or on a classical chip, I can store more data based on how many more transistors that I have. Whereas the other type of scaling is area loss scaling, where the subsystem entropy grows proportional to its boundary. Okay, so let's just consider different subsystems again as an example, but we can have subsystems that have equal volume and equal boundary. Again, boundary is the number of bonds that the subsystem has with the rest of the lattice. Again, this is another example where volume is 4, boundary or area is 8. And then this is an example where the volume is 6, we have 6 qubits and a total of 16 bonds with the remaining of the lattice. And by seeing how my entanglement entropy changes as a function of volume or area, I can essentially quantify or extract a volume entropy per site SV and an area entropy per site SA. Now, doing this for different for states that I generate with different drive detunings, I can see that as I go from the center of the energy band, which are states that are generated with delta is equal to 0, closer to the edge of the energy band, my SV, my dependence on volume, system volume drops, and my SA increases, or my dependence on system area or subsystem area increases. Now, I can look at the ratio between SV and SA, and then the trend becomes very clear. So at the center of my energy band, I'm clearly, my quantum state is clearly following volume law entanglement scaling. Whereas as I get closer to the edge of the energy band, I see an onset of area law-like scaling. And that brings us to the conclusion of this work, where we observe a change from a volume law scaling to an onset of area law scaling, entanglement scaling within our system by generating states that are either at the center of the energy band and moving them closer to the edge of the energy band. So with that, that brings me to my conclusion. I'm not going to go through every bullet point here. I'll just leave it here and maybe I'll answer a couple of questions. Thank you so much for your attention.
Thank you very much, Amir. Let's thank him, everyone. All right, so yes, the talk is open for questions. Raise your hand or send a message in the chat if you want to ask a question. People are quite shy today.
I can ask a question.
Yes, go ahead.
Yeah, because I missed really the first maybe 2 slides of your talk. So, so in your system, so do the qubits then are fabricated with the same frequency? I mean, with having in mind the same frequency?
Yeah, that's a good question. So maybe let me go to basically this slide. So our qubits are designed to have the same sweet spot. Well, I mean, they're designed to be actually nominally identical. However, there's some variations within fab. So we see a variation of roughly like 200 to 300 megahertz within our sweet spot frequency. However, for all of our applications, we want our qubits to be ideally for the dynamics I want to see biased at the same frequency. So that's why we went with the design choice that we did.
Okay. Okay, thanks. And
Yep.
Okay, thank you.
Yep, thank you.
if you have another question, Giovanna, you can go ahead. I
have a small question.
Oh, there's someone else. Yeah.
Yes, someone. Okay, Anegban, please.
Yeah, so I just want to ask that, can you briefly explain why the entropy was maximum at the half of your sample size?
Why entropy reaches why entropy is maximized when the subsystem size is half, right? So,
yeah.
So what I mentioned here is that if there's maximal entanglement, or this is basically before I introduce a volume law scaling concept, the entropy will grow as a function of volume. Now, if I have a subsystem, right, that's half my size, and the size of both subsystems are equal. And again, the entropy of, let's say, like, you know, the subsystem on the left has to be equal to the entropy of the subsystem on the right side, because we're in an overall pure state. But as the size of, let's say, the entropy on the right gets larger, then the size of the subsystem on the left becomes smaller. So now you're always limited essentially by the volume of your smaller subsystem. It's like subsystem and then the complement. So when they're both equal, that's when you expect to get maximal entanglement entropy. Whereas as one gets larger, then since the complement gets smaller, your overall entanglement entropy of your system goes down. So this is why I see this like curved behavior.
Okay. Yeah.
Thanks, Amir. We have to move on to the next speaker. So yeah, thank you very much.
Okay, thank you so much.
And next speaker is Dennis Willsch from RWTH Aachen, right?
And Jülich, basically, in the meantime only.
Right. So yes, Dennis, please, you will tell us about some interesting deviations from the standard Transmon model, if I'm not mistaken.
Yes, indeed. Can you see the screen?
We can see the screen. I think the sound is a bit low. Like we hear you, but it's a bit low. Maybe the mic is a bit closer to you, or
yeah, I can tune it up a bit. Is it better now?
That's a little better. Yes, you can turn it up more if you want.
Yeah. Okay, give me 1 second.
This is
like
good.
This.
This is perfect. Yeah, thank you.
Okay, very good. Okay, so yeah, thank you very much for asking me to present our most recent work here in this context. So the title of this work is Observation of Josephson Harmonics in Tunnel Junctions. And this story is about a problem. It's about a problem in describing and modeling the very basic element that lies at the heart of our superconducting quantum technologies, namely the Josephson junction. So the Josephson junction is basically two superconducting leads, usually aluminum, and an insulating barrier in between. And the current through this barrier determines most of the properties that we can use to build qubits, for instance. So the Josephson junction goes back to Brian Josephson, who in 1962 predicted this current phase relation, for which he later on got the Nobel Prize. So a sine phi current phase relation, which we use in our models, usually nowadays in the Hamiltonian as a cosine phi term, whose discrete energy levels should describe the discrete states that we can probe and use in the experiment. Now, what this story is about is actually that this model, if we keep it like that, spectacularly fails in describing our experiments. And we will look, as the talk unfolds, into what actually should come here on top of that. So, but first, let's ask the question, why should we care? So the Josephson junction is not just important for superconducting qubits, but also for material science and metrology. For instance, the definition of the current and voltage standard relies on the Josephson effect. And then there is, of course, quantum amplification, quantum detection, and quantum information, which we use for qubits. So now let's look at why this model fails and what should be there. I mean, as a matter of principle, actually, all models are wrong, right? It's just that we have reached an experimental expertise in design and precision so that we can actually see what else we need to include here. So we use Transmon qubits simply because they are widely available across the globe. So we cannot just focus on one single experiment, but test several experiments. And a Transmon qubit basically consists of a Josephson junction and two large capacitor plates on both sides. So this would be an equivalent circuit diagram. And from this, we usually derive the standard Transmon model Hamiltonian, which includes the charging energy and the Josephson energy. And the discrete eigenstates of this Hamiltonian then should relate to the eigenstates, to the discrete states we can probe in our quantum system in the lab. So we usually plot it like this. We have the ground state as the 0 state and the first excited state here. So these two are our qubit states. And then, of course, in a Transmon qubit, there are more states, the 2, 3, and the 4. And in our community, we've, of course, for a long time assumed that this spectrum is well described by this Hamiltonian. And when we found some deviations, when we were trying to model experiments, we were asking, is this actually the case? So to test this, we should perform the most basic quantum physics experiment that we know how to probe discrete transitions between states, and this is spectroscopy. So here you see for the first sample that we looked at, on the x-axis, the transitions from 0 to 1, the qubit transition, up to the transition from 0 to 6. And here we compare the model frequency, so computed from the eigenvalues of the Hamiltonian, minus the experimentally measured frequency. And you see already at the 0 to 3 transition, the model is off. And if we go up to the 0 to 5 transition, we go into regime. So here the scale changes from linear to log scale into like 100 megahertz to even 1 gigahertz, which is certainly observable where there are deviations in the model. So then, of course, we thought, okay, this is a single device, single experiment. So we measured the same device over successive cooldowns, and we found the same systematic deviations, a bit weaker now because the device has aged a bit, but still it's there. But of course, again, it's now a single experiment. So in a single lab, we looked into other experiments too, and we found, for example, here is a sample at ENS Paris, a very deep Transmon that we can accurately measure into the 0.6 transition, the same systematic deviation to the differences between eigenvalues from the Hamiltonian. And then there's a very interesting setup at the University of Cologne in blue here, where they have a frequency tunable Transmon, which yields in principle such data sets for a large range of magnetic fields that we can apply to the setup. One data set is shown here, but okay, these are all single qubit devices, right? So we also looked into multi-qubit devices, and here we took the 27 qubit IBM Hanoi device, for which we see that all the qubits here show the same deviation from the level 0.3 on, from the transition 0 to 3 on. Now it goes largely into the other direction. This is simply because these Transmons are a bit shallower. So we can only measure them, for instance, until the 0.4 transition. But the bottom line is this model basically fails to describe the levels that we can probe experimentally. So what is this model actually if we take into account terms that I have not written here? This is the standard trans model that goes back to the famous paper by Koch in 2007. And this, of course, also includes offset charges and the readout resonator. And in all the results that I'm showing, we have actually also included the readout resonator simply because it's the first thing that's basically that couples most strongly to the Transmon qubit. But the result remains the same. So there are these deviations here. So then when we found this across several labs around the globe, we tried several ways to fix this. The first is a series inductance. So of course, if we look at how the Josephson junction in this context is constructed, there is actually a linear inductance in series with the Josephson junction, so a linear inductance L, which of course we should include, right? And we haven't included that yet. And actually it turns out that if one does this properly, does the circuit quantization with all, like carefully with all the steps necessary, we can actually already predict harmonics, so higher terms like cosine m phi terms from the linear inductance. But we know the size of this inductance from HFSS simulations. So we know the geometric inductance, and it's much too, the EJM coming from this correction are much too low. So here we determined, or we concluded actually, series inductance cannot fix the discrepancies that we observe. The second thing that we looked at was hidden electromagnetic modes. And most of these devices on top here are in 3D cavities. And this is a three-dimensional geometry where for sure there are more electromagnetic modes, more than one harmonic oscillator that I include here. So we also try to include additional modes. They are called dark modes here. But also here, including these modes could not fix the discrepancy. Then we included the coupling to other transmons, which is particularly relevant for the IBM qubits, for the 20 qubits down here. And they're included in the diagonalization also the transmons, the neighboring 3 to 4 transmons for every qubit, but also this could not fix the problem. So our attempts up to here didn't work. So we thought, okay, actually we have to look a bit deeper into how current actually flows, how the Josephson junction actually looks like. And this is what we then did in the following. So current through the Josephson junction is carried by Cooper pairs because they are superconductors, and the tunneling processes from here to here through the insulating barrier are electron tunneling processes, and they are described by individual conduction channels. So each of these conduction channels corresponds to one transmission probability of the electrons from here to here. And the final supercurrents through the insulating barrier is then a sum of all the individual currents from these conduction channels. And if we look then into the theory a bit more deeply, we find in a paper by Benaka in 1992 already that the current phase relation caused by a single conduction channel takes this form. So already here, it's basically already expected that it's not just the sine phi contribution, but it's renormalized by this denominator here. So we can do a Fourier decomposition of this term and then look into the contributions of the higher harmonics that are already expected from theory. Then we find this, it basically depends on how large these transparencies, these transmission probabilities are. And basically in the superconducting qubit community for tunnel junctions, it's been assumed for a very long time that they are very small. So if we really take like 10 to the minus 6, and then we have approximately 10 to the 6 of these conduction channels, then we find that the sine 2 phi contribution is on the order of 10 to the minus 8, so not observable. So that is why the single sine phi relation was a good idea to start with. But if we now have a few conduction channels with a high transparency, we already see that there is a significant sine 2 phi contribution here. Okay, so with that expectation in mind, we looked into how these Josephson junctions are fabricated. And here is a STEM image with atomic resolution where we can really see the individual columns of aluminum atoms in the top aluminum grain, then the aluminum oxide barrier in between, and the bottom aluminum grain. And then we simulated the fabrication process of how these junctions are grown with shadow evaporation. And we used molecular dynamics simulations where we basically shot these aluminum atoms onto the substrate, and then they crystallize in an FCC lattice. And we took 2 examples, one the orientation, the 100 orientation, and the 111 orientation, simply because these are both extremes or 2 extremes, and we just don't know how the aluminum lattice is actually oriented. But independent of how we do this, we then also simulate the oxidization process with the oxygen atoms, and independent how we do this, we always find here already on this level some inhomogeneity. So the junction is not very uniform, not very homogeneous, but it has these bumps in here. And from a mesoscopic model of tunneling through an inhomogeneous barrier, where we took like a very simple model of a Gaussian thickness distribution. So saying that the thickness D varies with a Gaussian with median D bar and some standard deviation spatially. If we carry that out, this calculation, we already see that from theory, we expect several % of sine M phi contribution. Okay, so with this in mind, we now use the same experiment to test our new model. And indeed, if we include up to 4 of these Josephson harmonics, we can get a very good agreement for all the experiments shown here. But the question is now, these harmonics are probably not unique, right? In principle, we can include as many as we want and to get it all right. So what we then did is we tried to characterize all the models that are compatible with our measurements. And this is shown here. So here we plot the Josephson harmonics, the EJMs that can describe our experiment. And whatever model we find, it should be between two physical limits. One is the limit of a homogeneous barrier, the typical assumption where we have like 10 to the 6 conduction channels with very low transparency, which would yield the standard sine phi current phase relation. And the upper limit is the quantum point contact, which also whatever model we have should not exceed. So one model that we found is this one. So we have EJ2 here, EJ3, EJ4, EJ5. Another model is this one. And then we found another model, which is this one. And another model, and another model. And in the end, we then did an exhaustive scan over all the models that are compatible with our experiments. And then we find this result, which tells us that whatever model we have, the EJ2 contribution for this particular experiment here has to be larger than 1%. So there is no model that can describe the experimental data with an EJ2 that is smaller. And the mesoscopic model that I just introduced with the Gaussian thickness distribution, for instance, would lie very well between these models. And this model is interesting because it parameterizes all the EJMs, so all the higher harmonics, in terms of only two parameters, namely the average barrier thickness and the standard deviation. And the average barrier thickness for the kit device, for instance, came out as 1.6 nanometers, which is well compatible with the STEM image that we have. And the standard deviation is 0.4 nanometers. So we did this procedure for all the experiments under investigation. And we typically get this picture. So for all these experiments, we have EJ2 larger than 1%. And in particular, you see up here the IBM Q0 of the IBM Hanoi device, which has to be described with a very large, close to the point contact limit magnitude of higher harmonics. So this was one aspect of the study. So yeah, we now expect that our energy levels are, yes, Anton?
You are running a bit low on time. So
oh yes, yeah, it's just one more aspect. So we now see that the levels are shifted, but why should we care, right? Because we can fit this anyway. But the second relevant aspect is charge dispersion, and this already affects the qubit transition. So charge dispersion is the variation in one energy level for two branches where one quasi-particle tunnels through the junction. And this is exponentially sensitive to the Josephson energy. So we thought this is a very good test for our new Josephson harmonics model. So here we took the current qubit, which is measurable as a function of an external magnetic field. So we can get many data points for the charge dispersion, which is measurable then here for the 1, 2, and the 3 level. And if we plot the standard Transmon model in comparison, we see that it's off by a factor of 2 to 7. And if we plot the Josephson harmonics model, then it can describe all the 200 points very well. So the conclusion is of this study is for the theory that from now on, the superconducting qubit community also has to include, in principle, these higher harmonics in the established models. So there are a lot of interesting problems coming out of this. And for experiments, the question is, can we engineer these harmonics? Is there an optimal range of where these harmonics have to be put? Should we strive to grow barriers very close to the homogeneous limit, or might it be advantageous to be up here? So these are all questions that will need to be cleared in the future. So with that, I would like to thank my co-authors very much and also the audience for your attention.
Thank you very much, Dennis. Do we have questions from the audience? We have time for one or maybe two. Raise your hand. Or
Yeah, I have a question. So
yes, go ahead.
yeah, so as you said that, I mean, you are going towards this homogeneous line. So if you can, did you look into it? How will you achieve in experiment this approach?
Yeah, the question is whether we should go towards this homogeneous limit. I don't know the experimental best strategy to go towards this limit, But what I can say is it might also be advantageous to maybe engineer the harmonics to be up here, because I have this in a slide at the back here, right? You see the charge dispersion that I showed for the Köln qubit up here was is much larger in the experiment than the standard model predicts. But if you are very close to the quantum point contact limit, for instance, and there are papers on that out already, then you can also reduce the charge dispersion as compared to the standard transfer model. So the standard model is always this number here, and the bars are all the Josephson harmonics models. So how to best do this is probably for the future experimentalists to figure out. But there are regions also with harmonics which are advantageous for practical superconducting qubits.
Okay, thank you, Dennis. I think in the interest of time, we need to move on to the next speaker. But I guess maybe there's possibility to ask you questions in the chat.
Yeah, thank you very much.
Okay, thank you again, Dennis. And then the next speaker is Andrea Rodriguez Blanco, who will tell us about how to characterize the performance of trapped ion quantum error correction. So, Andrea, please. I don't think we hear you. I don't hear anything. I see you speaking, but I don't hear anything. Okay, I guess Andrea is trying to log out and log back in again. Tried and tested method for troubleshooting.
Hi, can you hear me now?
Yes, great.
Okay, sorry about that.
No problem.
Okay, let's go then.
Whenever you're ready, you can share your screen.
Okay, can you see the screen then now? Yeah.
I see the screen, yes,
Okay.
and I hear you well. Full screen mode there.
Yeah. Okay, so, well, hello everyone. My name is Andrea Rodriguez Blanco. Thanks for the organizers to invite me. Well, I just recently joined as a postdoc at UC Berkeley under the supervision of Birgitta Wale. But today what I'm going to do is to talk about the work that I was doing during my PhD about the characterization of the performance of quantum error correction circuits with trapped ions. So one of the motivations is like nowadays we have well-characterized methods to study the performance of physical qubits. No, we can determine the T1, T2 times. We can also infer about the performance of single and two qubit gates using process tomography or randomized red marking protocols. And in the further end, we have this certifying of quantum advantage, where we have new algorithms or validation concepts, and we try to prove if the output state of my quantum computation cannot be reproduced classically, no? And for that, we have some measures as the cross-entropy benchmarking or the cross-entropy benchmarking fidelity. Okay, so one of the questions is what about the characterization methods for medium-sized registers, no, for these near-term devices. And in many cases, what happens is like we assume like we have these well-characterized physical qubits, these two single and two qubit gates, and we put all together in an integrated system, and there are no more errors. But it is important to consider also how these minimum errors on the gates propagate through the circuit, and which is their effect at the end. So in near-term devices that has limited resources, it will be good to have some sets of experiments and characterization protocols where we can just integrate the information that we have from the individual elements and also the performance when they act as in the whole circuit. So in this talk, we focus on the characterization tools of these quantum error correction primitives that are the parity check measurements circuits in trap ions processors. These parity check measurement circuits, in particular, we are going to focus on the stabilizer quantum error correcting codes. This, like a stabilizer encode code, encode n physical qubits into k logical qubits, and then the stabilizer code is defined as the +1 or the subspace of m minus k commuting poly operators. And D, that is defined as the distance of the codes, is the minimal weight of a poly operator that will cause an error that cannot be detected by the code, sometimes also referred as a logical error. In particular, we are going to work with topological color codes with the smallest one, that is the distance 3, that matches with the STING code. And in these topological codes, the qubits are arranged in a planar lattice, and also the stabilizer measurements have local support, so that is really convenient for experiments. And in particular for the color codes, it's like the physical qubits are arranged on the vertices of the 3-colorable lattice. And here you can see for each color plaquette, different color plaquettes, you have an X-type or a C-type parity check operator. But also for the fault tolerance theorem, we know that it is important to ensure that these measurements are fault tolerant. It's like T errors happening on the circuit propagate at most as T errors in another code block. So this means, like if, for example, we want to measure the X-type parity check that corresponds with this circuit on the left, figure A, okay, if an error happened on the syndrome, in this case, on the ancilla qubit, it will not be detected by it, and it will propagate as 2 errors on the data qubits. So that design is not fault tolerant. In the image on the right, in B, we have add as a flag qubit that what it does is like if an error happens on the ancilla qubit, it can detect it. It will be flagged, this qubit will be flagged, and we will be able to discard the measurements that we infer from the circuit. So these flag qubits are really good for detecting these huge errors that are errors happen on the syndrome qubit that proliferate to multiple errors on the data qubits. There are other options to construct fault tolerant parity check measurement and designs, but we are focusing in this particular one because the qubit overhead is pretty small. And for ion qubits, in this case, we are going to choose, we pick the calcium 40 ions. The qubits are encoded in the Siemens sublevel of the ground state. And usually they have a splitting of 10 megahertz that is caused by external magnetic B field. We see here the 397 nanometer laser light for the dipole allowed transition that allows optical pumping, detection, cooling. Also, we have for the same wavelength that will allow us to do Raman transition and single and 2 qubit gates. And we have also other kind of wavelengths, more for selving or repumping purposes. In this work, we are going to particularize to laser-based gates and with a main focus on these 2-qubit entangling gates, because we have seen that for the parity check measurement circuits, we have this sequence of CNOT gates, but when we pass to the native trap ion gate set, there will be also kind of a different type of entangling gate, but these entangling gates are the major bottleneck to achieve fault quantum error correction near subdrug thresholds. So we are going to focus on how to build these entangling gates to get the error, the characterization of the error in this type of gates. And this disentangling gates with trap ions are called light-shift gates, where we use Raman lasers. Each ion has a pair of Raman lasers. These are non-compropagated lasers, and they are far off resonant from the dipole allowed states. Some of the conditions that have to be fulfilled is like the detuning is much bigger than the frequency splitting, also that the detuning is much greater than the line width of the transition, and then the conjunction of these laser beams will give rise to a collection of AC star seeds. Some of those, as in the picture on the left, is like the ion virtually absorbs and emits a photon from and into the same laser, but we will also have some cross AC starseed effects where the ion absorbs from one laser, virtually absorbed from one laser and emit in the other. I said virtually because the goal here is not to couple the population to the P states. No, we are just virtually populating. Okay, I think that I will not have time to review this. Just to say, like, this light matter interaction leads to an uncoupled Hamiltonian with the internal states and the motional state of the ions in the trap, but this energy splitting of the initial qubit now has some additional terms that corresponds to the differential AC star seeds, that is just an energy seed, but also that are the ones coming from the crossbeam oscillating star seeds that leads to this term. And on the other hand, the part that is the interaction Hamiltonian, it will lead to some state-dependent dipole force that will allow us to get disentanglement. Well, we have to fulfill, so if we move to interaction picture, we can extract the time evolution operator, and then we have similar to the moments of reson gate, we have a part that corresponds to a residual qubit phonon entanglement that we have to remove to avoid that remaining entanglement, and the spin-spin coupling. That is what we are interested in, just the spin, just entanglement between the spin states. We have to fulfill some closure relations, but just for you to know, like at the end, well, we have kind of what we see here. That if the gate timing has to be multiple of the detuning of the gates, and to achieve these gates, the bit node frequency of the lasers has to be set close to one of the trap frequencies of the motion. Sorry, like this is too much, and I think we don't have time. So to quantify the performance of these light shift gates, just to say that we are going to use the average gate fidelity, and to compute it, we are going to use it. We are going to compute first the entanglement fidelity that is defined like this in the second equation, that then relates quite easily to the average gate fidelity. And from the average gate fidelity, we will infer the infidelities for this gate. We do the analytically study of all the error contributions without taking approximations. We add perturbative methods, some master equations, and we get the analytically error contribution for different sources, from thermal errors of resonant couplings, the phasing noise, and residual photon scattering. And then with this, we can, so if we consider that these errors are small, the effect of this source of noise can be additive. So we can add the total infidelity of this gate due to all these errors can be inferred. Using, so if we plug some real experimental data, we can infer these errors. Here we have to say, like, the gate infidelity values goes from 10 to the -2 to 0.3, which are farther away from the fault-tolerant regimes that we need for fault-tolerant quantum error correction, but it will be useful for some of the characterization methods that we use later on. Okay, so just coming back to the parity check measurement circuits that we are going to use with trap ions, and in particular the entangling gates used between data and the syndrome qubits are these light shift gates that we are now well characterized using microscopic a microscopic Hamiltonian study. We want to use a benchmark to characterize these parity check measurement circuits, and we are going to use the capacity to generate entanglement. Let's put an example to see why this capacity of generate entanglement is at the heart of parity check measurements and quantum error correction. So imagine this small portion of the surface code, okay, where we have A and B are two data qubits, and then we have two syndromes that are for X for the X type measurement and C type. So we can start with an initial state like this, an arbitrary initial state for the two qubits and the two syndrome qubits initialized in the ground state. We can then apply all the sequence of gates, the CNOT gates and Hadamars, and we get at the result, we get to this output state. But and you see, like we have here the four Bell states for the two data qubits, and then the two syndrome qubits are in a collection of ground and excited states. So by measuring the syndrome qubits and post-selecting on plus or minus, we can get as an output state any of the four Bell states. Okay, so we can verify then if we take one of these output state and run it and introduce it again as an input in the circuit, we will say like we will get the same entangled state because it is stabilized by XX and CC type operators. But what is important here is like we can use this parity check measurement circuit to generate multiple partite entangled states, which are stabilizer states of the code. So that's the reason for us to study the ability of these circuits to generate entanglement as a benchmark. However, well, these genuine multipartite states are states which are entangled within all bipartitions. Okay, so more formally, we say like quantum state is biseparable if it can be written as a tensor product of two multi-qubit state, but if it cannot be written as that, is a genuine multipartite entangled state. However, the certification of these genuine multipartite entangled states grows exponentially with the number of subsystems. So for example, here we have, instead of the 2-qubit example that we wrote, we have a 5-qubit GSE state, and you will have to certify genuine multipartite entanglement in 15 bipartitions. So it's not really practical. So we can use we can try to find ways to make it more efficient, and one way is to use entanglement witness, like it's an observable that when the expectation value of that observable for a separable state will be 0 or greater than 0, and if that state is entangled, the expectation value will be negative. So we can think about constructing this entanglement witness operators using the stabilizer states coming out from the parity check measurement circuits. So so we have sorry?
You're running a bit low on time now, so you should try to do this.
Okay, so well, so we can construct the witness as you see here using the a stabilizer state can be determined by all the elements of the stabilizer group. So we use it to build our witness as a project-based witness, and then we have what is called the entanglement test operator. Well, so what we did is there are several types to characterize the performance, different types of entanglement test operators, and we have the standard multipartite entanglement witness that is more where the number of stabilizers grows exponentially with the number of qubits. Then we have the standard linear that is reduced just to measure the generators of that stabilizer state, okay, but it has the cost that maybe it is less robust against noise or is less finest. And then we develop also the conditional linear witness that is also linear in the number of grows linearly in the number of measurements, but you have to use techniques as localizable entanglement. But we proved that it was more robust than the standard linear method. Okay, so for example, here the performance of parity check measurements where the output was a 5-qubit state. From left to right, we have the standard, the linear, and the conditional one. And we say that when we use a phenomenological noise channel, well, we can see, so the blue dark areas are the ones that where we say like the test is inconclusive, okay, and the other ones are where we have detected a genuine multipartite entanglement. So, so for example, if the error, we can see like in general, the 0.5, 0.8, or 0.5 are the entanglement thresholds. And well, we can see like the conditional method is linear in the number of measurements, but it's also more robust against a noise. We also tested the performance experimentally, and in this case, are we just going to show the results for a 4-qubit state? Well, this was the output of the circuit, but here we project it on the syndrome as well. So if we project it on +1, we get this 4-qubit output state. If we project it in -1, we have this orthogonal state. And we measure the stabilizers. So for this state, these were the stabilizers, and we built our standard linear witness, where the entanglement test operator is just the normalized add of all the generator operators. And we observe that, for example, for the +1 projected output state, we have a witness of -0.14 and for the other case, so in both cases they were by more than 10 standard errors below 0, so we could certify this. Well, so we don't have more time, I think, but one of the things was now in all these previous studies, we introduced errors where phenomenological or just two-qubit depolarizing of the phasing noise, they are characterized by probabilities that is just a single random value between 0 and 1. So what we did in next studies was to relate this P error probability with the error that we got from microscopic error modeling from the light sheet gates, and then we fed that into the same simulations. So I don't think that I have my time for that. So yeah, just to say like we fed it. Yeah, sorry about that. We don't. Oh, sorry. Yeah, I don't know if I have. I should stop now, right? No.
Yes, please. If you have a conclusion slide, maybe you could put that up.
Yeah. So well, just to say the conclusions of the study is like, well, we have characterized trap-ion circuit by the ability to generate multipartite entanglement, and we observed that well, sometimes one could overestimate the power of the fault-tolerant design, in this case the flag fault-tolerant design, if used, for example, a depolarizing channel, because, for example, for low error rates, you will say, okay, the flag, the fault-tolerant design is valid, but when this error rate increases, the fault-tolerant, the flag cannot cope with errors, no? So it is important to include these realistic, more realistic error models to realize, to be aware of these aspects. And also that is important, you can modify the stabilizers of your circuit to be biased against the noise model. If you know you have a better understanding of the noise model on your system, you can use different stabilizers that are more biased against that noise. So that is a big motivation for us to include more realistic noise modeling in these circuits.
Okay.
Thank you for that.
Thank you, Andrea. So I think in the interest of time, we have to forego questions, but of course, if you stay on for a while, there's the possibility to ask questions in the chat. So then the next speaker is Shuxiang Cao, who will tell us about how to use multi-level transmons, 4-level transmon qudits. So
Sorry, I forgot to unmute.
Yes, I was just going to ask you.
Okay, thank you very much for organizing this event. And I'm Shuxiang. I'm Shuxiang from Oxford, University of Oxford, and today I'm going to say a little bit more about my recent work about using a 4-level subspace of the Transmon to emulate 2 qubits. And I have put the QR code here, so if you're interested, please have a look at our manuscript. Yes, so motivations. Why would we want to do that? So the traditional way we build quantum computers are like we find some 2-level systems such as spins, and we tile them up, and in the end we get the computation space to be the size of 2 to the n. But however, if we have a d-level systems, and then we tile them up, then the total computational space would become d to the n. So that is much larger than the qubit-based quantum processors. However, why it hasn't been put into standard practice? The first is the multi-level quantum systems are more difficult to build and operate. And usually the higher energy levels are susceptible to noises. And also the algorithms we have developed are not really for these qubit-based quantum processors, and you will have to make some changes to the algorithms to make sure they can utilize the full Hilbert space provided by these qubit-based quantum processors. So the way we solve these 2 problems is first, we build better hardware that can cope with those noisier higher levels. And also we emulate the qubits using qudits so that you don't have to do much about your algorithms while you can still run them on the quantum hardware. Okay, so let's say this is the Transmon Transmon eigenstates, and we map the lowest 4 levels into 2 qubits, which is shown here. And then based on this mapping, we can define 2 virtual qubits, let's say QA and QB. And then the single qubit operation on the virtual qubit A can be translated as 2 consecutive single QD gates on the Transmon. So you basically do 2 consecutive pulses on the 0-1 subspace and 2-3 subspace. And then if we want to run some gates, single qubit gates on the virtual qubit B, then the strategy we're using is we first swap qubit A and qubit B, do the operation on qubit A, and then swap them back. So it is worth noticing that implementing this swap gate is rather simple on this qubit-based mapping, where you just need to drive a physical pi pulse between the 1-2 transition followed by 2 virtual Z gate to correct the phases. So that's very, very handy. So now I'm going to talk a little bit more about the architecture we have in Oxford, which is quite different from those standard 2D plane circuit QED. So here we have our qubit and resonators printed on both sides of the substrate, and the qubit is coupled to the qubit control pin capacitively from the top, and then the readout is coupled to the readout pin from the bottom. So in this way, we don't have to do any wire boundings to operate our qubits and implement readout. And this is the device we made. On the left picture, we have bulk half aluminum, which is like the cavity we put our chip in. And the small pieces above it is the readout multiplexer. You can see we only have 1 coaxial cable connected to it. And then so this enables us to read all 4 resonators within on this chip. So on the right is a photo of our chip, and for this device we actually built 4 qubits and 4 resonators on the same chip, but they are not coupled to each other. So we just chose the one that has best coherence and demonstrated this experiment. So here's some coherence statistics, and So we are pretty happy about the coherence we obtained on this device, as we didn't use fancy fabrication techniques. Everything is done with the standard procedure with aluminium, no interesting methods, extra methods. So, and for the 2-3 subspace, which is most susceptible to the noise, we still find it has like 87 microseconds T1 and 35 microseconds T2 echo, and which we conclude it is enough for us to implement some variational algorithms. So it is also worth discussing that we actually slightly engineered our readout resonator so that we have our resonator line width equals to twice of the chi value, which is the state-dependent resonator frequency shift. Here, actually for the multi-level systems, the chi shift is not identical. As when it goes to the higher levels, it doesn't shift with the constant value, but it will change a little bit. But here we just say we engineered our kappa to be twice as the chi shift between 0 and 1 state. And this is the some plots of our single shot readout. As you can see, we have a very decent separation between all these blobs, considering we actually don't have any quantum amplifiers within inside our readout chain. So we're very happy about this result, and we hope to improve it by adding 2PA or JPAs. Okay, so one thing you might immediately want to ask is, okay, so you got your 4-level system, and in fact, the Transmon qubits are more susceptible to the charge noise on the higher levels because it exhibits a rather large charge dispersion. And to characterize this effect, we have done the Ramsey experiment for like an hour and a half, and to find the frequency of the 2-3 transition. And here we find the charge noise induced the frequency shift, the dispersion is about 20 kilohertz, which is much less than our single qudit driving strength. So it is still in the safe range to operate our quantum algorithms. Okay, so here we also want to understand what's the spam error of our qudit. So here we implemented a gate set tomography on the 4-level system and reconstruct the measurement operators. And here we also find the readout fidelities of these four measurement operators shown here. And you can see, so each of them is showing that the fidelity to measure your state in the 0, 1, 2, or 3. And then you can see the two state. So the this operator and this operator, so they have some significant state misassignment, which we will come back later and discuss about it. And then another part is we reconstructed our initial state fidelity, which we find our initial fidelity is about 90%. And we have a rather considerable excited state population when our Transmon is at thermal equilibrium. To solve this problem, we implement the active reset protocol, where once we finish our readout, we would discriminate which state our qudit is in, and then send our reset pulses to bring it back to the ground state. So we left about 250 nanoseconds between the measurement pulse and the first reset pulse, so that we have enough time to clear the resonator. Then we apply the qudit pulses. So and the result is significant. We managed to significantly reduce the excited state population as shown in these plots. So each of so the first row is we're preparing our qubits, the transmon in the 0, 1, 2, and 3 state without the reset, and the second row is we're preparing them again, but with 3 times reset shown here. And then we use this resetted result, and we do the gate set tomography again, and we find we managed to improve our initial state fidelity to 99%, above 99%, and we are relatively happy about this result. And then we here we report the gate fidelity characterization from gate set tomography, which is shown here. And the first question you probably want to ask me is, why would the 0-1 transition has a lower fidelity compared to the 1, 2, and 2, 3? And we suspect that this is because we placed the LO signal for our qubit operation pulse that closer to the 1, 2, and 2, 3 transition, which leaves the signal at of the 0-1 transition at the very edge of our operation frequency band of our control electronics. So it's already at the very edge, so we could not synthesize a very good signal at that region. And then we, for the emulator, we did randomized benchmarking to find the Clifford gate fidelity for the virtual qubit A and B separately, while we also tried the single qubit Clifford gate fidelity together, as well as the 2 qubit Clifford, like here. So for the 2 qubit Clifford, we got about 90% fidelity, which is significantly lower. And we would like to comment that this is because this is an emulator, and we didn't optimize our gate sequence. And in fact, this is exactly the same gate sequence you would like to run for a cross resonance based 2 qubit processor. So this gives us the highlight that we need to optimize our gate decomposition to get the best performance of our emulate inside our emulator. Okay, so now we're moving to do the variational quantum algorithms. So this is a variational quantum eigensolver for solving hydrogen molecule, which has been demonstrated by Google in 2016. And the way it works is you run this quantum circuit shown here, which it only has one classical parameter you need to sweep through and then optimize its value. And the energy you're trying to reconstruct is by evaluating these 5 Pauli operators as measurement observables, and then you do a weighted sum, and then you got your energy. So we utilize this ansatz, which is exactly the same as the Google ansatz. However, we use this ZZ theta gate here to facilitate the entanglement, and this ZZ theta gate on the qudit system can be implemented exactly with the pure virtual Z gate. So that is very handy. So here I'm showing some results. These 5 plots are the experimental value extracted from the hardware, and the white line is the simulated ground truth without any noise. The red line is the average value from the experiment result, and the gray line is the bound of our theoretical value, which is just -1 and 1. And here, with this raw result, we can construct the energy versus bound distance plot here. And the shadow here denotes the standard deviation, the error bar. So now you can see some problem, like we are still quite far away. Okay, I'll be very quick.
Reach the conclusion.
So, okay, so it's still very far away. So want to figure something out if we can make it closer to the ground, to some error mitigation. So a little bit quick, and this is basically showing that we identified the arrow syndrome like. And so here is can be explained by the misclassification error, which was hinted by the previous gauge set tomography result, and also the amplitude damping error from the simulation. And then we first utilize, we remove the shadow. If you can see here, the first method you do the mitigation is to remove this shadow, which is explained by the misclassification, and it gets a much closer result, and you get a much cleaner plot of your expectation value, but it's still far from your theoretical results. And then we measure the assignment matrix, and then use the inverse assignment matrix to correct the assignment, the measurement assignment, and then we find it gives us much closer result to the ground truth, and it is closer to the. It has reached the chemical accuracy. So in conclusion, we build a very high coherence transmon with the coaxial off-chip coupling structure. And also we implemented randomized benchmarking and gauge set tomography to characterize the gauge fidelity and spam errors. And in the end, we demonstrated it can work for a variational quantum eigensolver, and the main error budget comes from readout error. I would like to thanks for your attention, and thanks also I'd like to thank to all my colleagues from Leak Lab in Oxford. And now I'm happy to take questions.
Anton, you are muted.
I just realized, yes. I was clapping, but you didn't hear it. We have time for one question, I think.
Can I ask a quick one?
Of course.
Maybe a naive one. So how do you construct the randomized benchmarking for your qudit gates? Did you separate the two similar to single qubit, or do you have one key for gate set for all your qudits?
No, so because we are trying to compare our emulator performance with some already existing 2-qubit device, so we just run the circuits for a 2-qubit device on the emulated by the emulator to characterize the performance. So it is not optimized for the qudit exactly. It just directly translated from the 2-qubit gauge sequences into the qudit sequence with that mapping we mentioned.
I see.
Before, yes.
Yeah. I have a very small question. So how are you incorporating the G numbers in your Hamiltonian? Are those the actual coupling numbers, or those are the fixed numbers?
Sorry, which number?
When you are showing the pulse sequence for the VQE, you showed the G, these right hand side.
Yes. So those G's are calculated by from some other packages, and they are parameterized by your bound distance, like the distance between two hydrogen atoms. And you can work out these G's by setting the distance, the bound distance of your hydrogen molecule. As you can see here, in fact, each of these dots we're using a different G, and they are parameterized by the bound distance. And you can just find it, for example, from the Google package OpenFermion or PySCF.
Okay, so these don't have any relation with your actual coupling strengths of the qubits, right?
No. This is for the algorithm. It has nothing to do with the physical qubit.
Okay.
All right. Thank you again, Shuxiang.
Thank you.
I leave the word to the last speaker of the day, or the evening rather. Thank you everyone for staying with us this late. So the last speaker of our session today is Liangyu Chen, also from our center here at our Wallenberg Center here at Chalmers University of Technology. And he will tell us about how to do Transmon qubit readout. So please, Liangyu, take it away.
Thank you so much for the introduction. I would say just also good to follow Shuxiang's presentation because we are using for a similar direction that use qudit to enhance our quantum computing capability, basically, and we are now using it for purpose of readout. So our work here is concerning Transmon qubit readout fidelity at to reach the threshold for quantum error correction without using a quantum limited parent amplifier, exactly using this high energy state and also multiple readout tones. Yes, so let's start with have a quick overview of our device here. We have 3 fixed frequency Transmon qubits, and each of them coupled to a readout resonator, and then all 3 of them coupled to a common Purcell filter that is embedded in the feed line. So we don't have any 2-pass JPA that quantum limited parent amplifier in the readout chain. Here is the optical micrograph of our device. So the green one you see here is common Purcell filter, and then the red are the resonators, the blue are the qubit on the other layer. So with the techniques we will send later, we achieve a 2-state readout fidelity of 99.5% by using the high energy levels, and a 3-state readout fidelity of 96.9% by using a 2-tone readout pulse. And all this is done within 140 nanoseconds of readout time. So we've shown here in this work that these techniques are robust and very straightforward to implement in any state-of-art superconducting quantum devices to enhance algorithm performance and anything can run in a circuit. So first, let's start with the transmission coefficient to 1 of our device. Here you saw the magnitude of S21 versus the probe frequency. Our qubits lies around 5.4 gigahertz, and our resonators are around 6.6 gigahertz. And the peak of this profile you see here is the center frequency of our Purcell filter. And in principle, our qubits should have a 20 dB suppression from the Purcell filter we have here. If we look a bit closer at the center resonator here you see the state-dependent response of the resonator when the qubit is at 0, 1, 2, or 3 state. So similar to what Shuxiang has shown in his presentation. And we are going to use this information to determine the optimal readout frequencies later on in our experiment. So here we want to understand our qudit state first. And for this, we prepare a simple T1 experiment, basically prepare 0, 1, 2, and 3 state, and wait for a certain amount of time before we measure it in the end. And for this, we can extract all these decay rates that happen between the levels, T23, T12, and T01. And since the non-sequential decay rates are small, we're going to ignore them for now, just to characterize these sequential decay rate first. And here are the measurement results. Here it shows the 0-state population as a function of delay time. And this is qubit prepared in the 0 state, 1 state, 2 state, and 3 state. Here's the zoom in of at the shorter time scale of the same measurement. And you see this is where we're interested in is the measurement time with around 140 nanoseconds shown the dashed gray line here. And to get a good fitting of the measurement data, we solve the system of rate equations consists of P0, P1, P2, P3, the population at each qubit state, qudit state now, and the sequential decay rate T01, T12, and T23. The solution for the green curve you see here, where the qubit is prepared in the 2 state and we measure population at 0 state, is as you see here. So it's a combination of 2 exponential decay, and these actually changes the behavior of the decay very dramatically. And instead of a exponential decay, it's now non-Poissonian. And the slope at the beginning at a very short time scale is actually closer to flat here, instead of the maximum slope you saw in a typical T1 experiment. And if you look at the blue curve here, where the qubit is prepared in the 3 state, then this formula becomes a bit more complicated, but the message is still the same. It's a combination of exponential decay that in the end, when they combine, the slope at the beginning is almost 0. So this we can already have indication that if we can use this for readout by moving the 1-state population up further to the 3-state, then we can reduce our readout error significantly at short time scale. So here, then we can compare the numbers from the fitted model and found that if we have pi1 2 pulse, we can reduce our readout error from 1-state from 2% to only 0.06%. And if we are a combination of both pi1 2 and pi2 3 pulse, then this error is almost 0. And we predict that we can achieve greater than 99% readout fidelity with these techniques without even using a parametric amplifier at this moment. So to characterize how good we can do readout, this is a simple readout calibration procedure where we prepare 0 and 1 state and directly measure. In this case, the most dominant error will definitely be the decay from 1 state to 0 state during the readout time. And to boost readout fidelity by reducing the error from state relaxation, qubit relaxation, we have this additional pi1 2 and pi2 3 pulse we discussed right before the readout. And then 0 state will stay at 0 after these 2 pulses, but 1 state will be pumped to 3 state before the readout. And then we'll have to decay through 2 state, 1 state, and back to 0 to cross a discrimination error. This is called the shelving techniques and have been explored very, very much in the recent publications. And then we can also include the pre-selection protocol to filter out any thermal population or the remaining population from previous measurement to get a to remove all the systematic errors in our calibration procedure. Then we can choose the optimal readout frequency to even boost our SNR further. To do this, we look at I and Q components of our S21 parameter, similar to what Shuxiang has shown earlier. That we can see that at this frequency we choose here, the 0 and the other high-energy state are very much separated. And this, when if decay happens from 2 to 1 during our readout, it will not change our discrimination result if we only look at 0 or not 0 state. So by choosing our primary readout frequency to be here, then we can do a very good job in discriminating between 0 and not 0. Here shows our measurement result. If we draw a line from the center of not 0 to 0, then we can project everything into a 1D histogram, as you see here. And then from here, we can calculate that our 2-state assignment fidelity is 99.5%. And the remaining error here is still coming from prepared 1 state, but misidentified as 0 state. So we think here is still due to our imperfect state preparation and such, or imperfect pi1 2 and pi3 3 pulse. And we do repeat this on all 3 qubits simultaneously on a chip, and found that we reduced overall error by around 57% on average with this shelving technique. And also the readout fidelity become more stable over time, suggests that this technique is more robust as well. So next, we want to also look at the techniques to discriminate between high-energy levels, since the 2-state population is also very important in identifying leakage in both gate calibration and error correction algorithm. So for that purpose, we select a secondary tone that's around here. If you look at the 2D plane again, then it gives the maximum separation between 1 and 2 state. And since 2 and 3 state are still indistinguishable at this frequency, then those two are lumped together as the 2 tilde state now. So 2 state here can still serve as a buffer for 3 state when decay happens. So to calibrate our readout fidelity, we basically prepare 0, 1, and 2 state now. And we add this secondary tone to our primary tone in a single readout pulse with a standard frequency multiplexing technique. And you also add this pi1 2 and pi2 3 pulse before the readout. So 0 state will stay at 0, but 1 state population will be shuffled to 3 state here. and two-state population will be put back to one state. So that for initial qubit population in one state, it can still have this two state as a buffer before decay can affect our discrimination result. So to understand the two results together, first thing we can do is to just discriminate them separately and then combine the results afterwards. So if we look at the truth table here, you have the first result returns 0, and the second result also returns 0. Then the final result just definitely to be 0. And if the primary result returns not 0 and the secondary tone return a 1, then it's the common factor among those. So the final result should be 1. And then that means the initial state is at 2. If the primary result is not 0 and the secondary result is 2 tilde, then the final result can be either 2 or 3 state, since this is indistinguishable, and the initial state should be at 1. And if these two tones, the result from these two tones disagree, like the first one returns 0, second one returns a 1 or 2 tilde, that means we have some sort of overlap error, and this is then discarded. This amounts to about 0.5% of our readout shots. Another way to do state discrimination is by combining the IQ component of each of the shots together. So we have a 4-element vector as an input, and we feed this into a feed-forward neural network with a 2 hidden layer. And this is a very straightforward training procedure, take only a few minutes. And then we output a probability for the qubit to be initiated at 0, 1, or 2 state. And from there, we can reconstruct our confusion matrix. So then here shows the result of our shots in primary tone and secondary tone. And we combine the IQ component from each one and reconstruct our confusion matrix here. And then we take the trace of this confusion matrix, and this gives us a 3-state readout fidelity of 96.9%. The freeway field neural network is also performing better than true stable, about 0.5%. So this is a result report with the feed-forward neural network. And a special feature of our technique here is that two-state population is more likely to be misidentified as 0 state than 1 state, because these are shuffled to 1 state before the readout. It's easier to decay to 0 than be excited back to up to 3. So this is larger. And compared to our single tone readout result, where we optimize the frequency to best distinguish 0, 1, and 2 state together, it has around 2% of improvement here. So this is very significant. Then in conclusion, to summarize, what we have is with the common Purcell filter chip and a 149-second readout time, we have achieved a 2-state readout fidelity of 99.5% and a 3-state readout fidelity of 96.9% without using the Conner limited penetration amplifier. And we will have to investigate other limiting errors, including the state preparation pulses and also the imperfect pi1,2 and pi2,3 shelving pulses. Since we have more photons in the cavity, we also want to investigate the measurement-induced mixing and what that will affect our performance. And also, relating to that, we also need to investigate the readout crosstalk and dephasing incurred by our technique. Future improvement also include having a pulse engineering scheme where we can compensate for the readout crosstalk and dephasing, secondly. And also, as Sean has showed, we need a reset protocol for these high energy levels, and it will be better to be unconditional as well. In the end, we also want to test how much we can push it even further when we have a tuple in our readout system. So here is the end of my presentation. This is the link to our news publication here. And he had the emails of our people that you can reach out to if you have more questions or comments. Thank you so much.
Thank you, Liangyu.
Yes. Doing well in time. Now open for
Very
questions.
well time. Yes. So we have time for 1 or 2 questions. just raise your hand, or well, maybe simply speak up if you have a question. There will not be a chance to ask questions in chat after this, because this is the last talk.
Yes, they'll shoot me an email if you have one afterwards.
That's of course a possibility. Maybe everyone is tired. It's getting quite late here in Sweden, at least. So, okay, thank you again, Liangyu, and thank you everyone who spoke in this session. I think we've had really a great selection of talks. I've learned a lot, and I hope you have too. So this was the end of the first day of this workshop. So today we focused on quantum computing and simulation. Tomorrow there is quantum sensing and communication, starting again at 2 p.m. I hope to see you there.
Thank you so much, Anton, for the organization.
Night.